know analog discovery, but I'm not sure about digital discovery.
Holy cow!
Oh, we're rolling.
What's that?
We're rolling.
Okay.
I'm running out of freebies already.
My goodness.
How did I do that?
I'm gonna change it to.
Yeah, perfect. Thank you.
Sorry, I'm running out of
Yes. Those are PMODs. Oh, no. Oh, those are.
That's what I got.
I'm not sure, actually. I haven't seen that before. I think they're touch buttons.
Uh-oh. First class and I'm out of freebies.
I'm guessing they're touch buttons. I'm not 100% sure, actually.
So, Keith,
Because I don't have one of those. I've never seen it
what are
before.
these guys? Yeah, they're touch.
So they look like touch buttons?
They're touch buttons.
Okay.
Pin out.
They're inductive and I'm sorry, I'm out of freebies. I can use them. It's like a Cracker Jack bottle.
Exactly. Okay. So I think.
Oh, the purple box. No, those are extra credit. All right.
So I think it's time to get started.
It's time to get started. This is the implementation of the OpenScope, 1 megahertz PIC32MZ based IoT Wi-Fi oscilloscope and more. 2103782. You have a survey form in front of you. Our survey ID is 374. It should already be on your survey. I would like to say, if you like the course, fill it out. I would like to say, if you don't like the course, don't, but we have to have you fill it out anyway. So if you don't like the course, fill it out too. We do want that feedback. So, let's get going here. Start on my thing. I am Keith Vogel. I work for Digilent. I am the one who designed the hardware and the firmware. Waveforms Live was done. One of my co-workers did Waveforms Live, which is the browser-based UI you will see. This is John Day, who works at Microchip. He's just a great guy.
You too, Keith. So I'm John Day. I'm a field applications engineer and technical fellow. I work out of Microchip's Boston office. And even though Keith is Digilent, and we live on opposite coasts, we both have, I've helped Keith as much as I could through the project development and been honored to have received unit number 1. So I've been using OpenScope. I'm the first guy to have gotten an OpenScope outside the company. And alpha, beta testing, and it's been a true pleasure working with you on this. And hope everybody has a total blast and learns a ton here. This is it's going to be a great class.
This is going to be a pretty intense class, but enjoy it. We can answer questions, but they have to be pretty quick because we've got a lot of material. There are a couple of other guys that are notable in this project. Larry Standage, I don't know if he's in here. He is Mr. MZ guru. He literally wrote the documentation on the MZ, which is the processor we have on it. A very good friend of mine. We're very close because we work very closely together. Keith Chamberlain is in the back. He helped me with this presentation. He was a beta tester. When I first, I didn't have a picture of him when I was first working with him. I thought he was about 55 years old, all involved. I ended up seeing him, he's just this great kid, and I love him. But Keith helped a lot with this presentation and reviewing, and he actually made all of the transition slides. So I really thank Keith for what he's done. The class objectives. John will show us how to use the OpenScope, and we'll talk a little bit about limitations in the design. I will go over the hardware design. We will talk specifically about how we doubled the speed of the ADCs by interleaving 2 of them. To reduce the cost of the components, it's got under $5 worth of analog components on it. To reduce the cost of the components, we did self-calibration. We use the DMA to offload the CPU. The CPU runs at 200 megahertz, and yet this thing will run all the instruments concurrently, including 1.25 megabaud on the UART. So we do a lot going on 200 megahertz processor, and we use the DMA to do that. We'll go over how I triggered the instruments and how I synchronized them. We did not put down a commercial DAC. We put down our own R2R ladder. It was about 1/6 the cost. And then how to communicate to the OpenScope via Wi-Fi and USB. You can do it either. It's a Wi-Fi instrument. You can talk to it directly to the instrument from Wi-Fi, or you can do it through the USB. It's all text-based protocol, so you can actually fire up TerraTerm or Postman, and you'll see this and communicate directly to it. And at the end, we'll show you how to build the sources. It will build both an MPLAB-X, and also we have an Arduino IDE capabilities to build under the Arduino IDE. So the agenda today is going to be full. John's going to do Waveform's live demo, which is the UI. It's how to use it as an application. I'll go over the architecture, how I allocated the resources in the MZ. The first instrument is the DC output. There's 2 DC output drivers to 50 milliamps plus or minus 4 adjustable. We'll go over that instrument, and then I'll talk about what needs to be precise and what doesn't. And of course, the whole point of this thing is not much has to be precise in the instrument. Just a few things like the references. I'll talk about the analog inputs, which are very simple. How I use DMA for parallel processing, because I had to do a lot at once on a processor that's not particularly fast. We'll talk about how I doubled the ADC speed by interleaving them. How we got the logic analyzer in there. This is a very hard topic, scope triggering, because I had multiple scopes that I had to synchronize, trigger, different sample rates, and then of course I had to get them synchronized across the various instruments. Then we have a waveform generator that is also on here. And because we use the DMA very extensively, we have to really understand how the DMA bus works, installing, how they stall each other, and how they trigger, and also all the interrupt priorities for the interrupt routines and their priorities. The USB interface is all done with DMA. We get 1.25 megabaud through it. The next version, we hope to get 5 megabaud out of it. And we'll talk about how we did that with that. Talk about the text-based protocol. We'll do some demos here where we actually talk to the OpenScope through Postman and through TerraTerm. And in the end, we'll talk about, okay, how do we build the sources? All this up on GitHub. You can download the projects. You can build it in the Arduino IDE. So it's all there, and we've already had customers do this, so we know it works. The features of the OpenScope, it's a 2-channel, 12-bit. We'll talk about this 2 megahertz bandwidth, 6.25 megasamples per second oscilloscope. It's 6.25 megasamples per second is really a 1 megahertz scope, but the analog circuit, it's the -3 dB point at about 2.8 megahertz. So marketing wants to call it 2 megahertz. I want to call it 1 megahertz, and that's where we're at on that. It's got a function generator. It can produce a 1 megahertz signal. It'll be down -2 dB at that point. It's a 10 megasample per second function generator. It's got 10 logic analyzer channel, and they're sampled at 10 megasamples per second. It's got 2 user programmable power supplies that will supply about 50 milliamps plus or minus 4 volts. John will actually use that to drive his metal detector that he made in the demo. You can communicate through Wi-Fi or USB, and all of the UI is browser-based. And its retail sale is $89, but you can buy it in the store today for $76. Here's a little view of the board. This is the pinout. It comes here. It comes with fly wires that plug in there. You have your 2 analog channels. You've got your function generator, and then you have your digital I/O for the logic analyzer back here. Going around the board, this is your MF24 for the Wi-Fi communication. We put down an FTDI chip for the UR communication, the MZ, of course. We actually used analog switches on the feedback of an op-amp for gain selection. We did not use a PGA. It was considerably cheaper to do this. And then over here we have some just amplifiers, Microsoft op-amps for some amplifiers. We're going to go into a demo. John's going to do.
Okay.
And John made this little metal detector. He actually used the OpenScope during its beta period to complete it, and he kept calling me up saying there's something wrong with the OpenScope, and I say, did you try it on your good scope? And he said, gotta fix my circuit.
Actually, it is kind of a funny story. So if you flip to the next slide, I just want to go over the circuit because it's kind of interesting to note what this circuit is when we demonstrate the OpenScope, just so we're all on the same page. And so, so I was doing a reference design. Everybody here know what CIPs are, core independent peripherals, which we have on many of our PICs. I was using an 8-bit part, in this particular case, 16F1704. And so we set up a classic LC tank circuit here with the built-in comparator. Didn't require any external components. And we had an op-amp off here, which is set up for a level detect, a peak detection circuit, which feeds into the ADC. We used a CLC to trigger a timer, and then we had a separate timer which set up a period of 3.9 milliseconds through a second CLC that triggered a capture compare register. And so all of this interconnection with no firmware at all, the CIPs automatically measured the frequency for us because of the LC tank circuit, because we had a fixed period of accumulating clock pulses within the timer one timer, and the number of clock pulses that we accumulated got stored in the CCP1 all-in hardware, and then we could display that later on. And we're going to show this. So the circuit was very, very simple. This was the whole circuit here. You can see there's basically no other external components there. This was the LC tank circuit itself, you know, the L and the C. Here, the L was actually a PCB inductor, and then it was AC coupled to a divide-by-2 circuit here, and then the comparator output was fed into the PIC, was fed in through this mode here, through this node. And then we had the PIC has a built-in op-amp, which we set up as a both amplifier, a gain amplifier, and this diode creates a peak detector for us. And then we fed that into an ADC. So I just want to familiarize everyone with the schematic as we show it. So these are some of the nodes that we're going to test out. So we'll take a look at the LC tank itself and its magnitude and its frequency. We take a look at the comparator output, see the square wave for that. The OpenScope actually has FFT built in. So we can run an FFT, and we can look at the base frequency, and we can look at both the LC tank, which should just be primary frequency, and then the square wave coming out of the comparator will do the classic 1/3, you know, 1/3 at 3 times the base frequency, 5 times the base frequency, and so forth. And you can see the FFT is perfect. And because it's a pretty high frequency, you can see the rollback too, which is kind of interesting. So it gives you some idea what the sample rates are. And then we can also take a look at the op-amp outputs as well and peak detect circuit. So, so with that, I think I'd like to change the, just give me a second here. So, Waveforms Live is the GUI, and it's actually a HTTP. It's served from the Digilent servers currently. So if you go to waveformslive.com, it'll pop up with a add device and a configuration menu that you see here. And in this particular case, I am connecting to OpenScope through the USB port. So there's a small installation that you have to do. It's called the Digilent agent, and what the Digilent agent does is it provides a HTTP port, which is a local host, you know, 42.135 on COM72, which is what the USB has enumerated as, and that provides the channel for which the HT browser can now communicate with the OpenScope. And so once you fire up this menu, you'll have the option of configuring it, and the configuration menu will allow you to select a device. You can connect to multiple OpenScopes at the same time, which is pretty cool. You can update firmware, so it has the ability to automatically detect if there's new firmware available. That's there as well. And because OpenScope can be controlled, or it can be accessed by either USB or Wi-Fi. So if you could build a mobile robot, for example. You could have a drone flying around in your room, and you can be measuring the motor current with OpenScope and looking at it on your phone because it's Wi-Fi. So these are some of the really cool things that you can do with this product. And because the Wi-Fi channel, could you maybe switch to the next slide? I just want to talk about communications just for a moment. And we're going to go into, Keith will go into extensive detail on this, but OpenScope implements a Json command parser, and that command parser can be commands like set the waveform generator to 100 kilohertz at 2 volts peak to peak with this offset, and then boom, it'll automatically start generating that. Or it can do things like set channel 1 at this sample rate. All the types of things you would do with knobs on your oscilloscope, those are all Json commands. And those commands can either come through, if you're plugged into USB, then the Digilent agent will provides that interface through the COM interface. But also, you can also go directly through the IP address through Wi-Fi once it's configured. And what's neat is you can have both running at the same time, because the command interpreter doesn't really care which channel it comes through. And we're going to demonstrate that in one of our last demos. Keith will control the scope through Wi-Fi, and I'll be demonstrating the scope through USB, and you'll be able to do that through both channels. And this can be very useful if you want to do test circuits, you want to have like a test harness, and you want to control your oscilloscope through some other program and get test results back. You can do that and just do that through the Json interface. So once OpenScope is configured, in this case, we can see we've already configured this. We've connected it to the Digilent router here, and we've gotten an IP address 192.168.1.110, and that's how you would connect to it if you're going to use the Wi-Fi capability. So once you've got it configured, then you'll connect, and once you connect, you'll see what you would expect to be a very standardized scope panel. Now, you can either connect through Waveforms Live through a browser if you want, and so it doesn't require any installation, or optionally, there are both Android and iOS apps that are available, and those apps will directly connect to. And there's a bit of an advantage of having the apps because it's native, so the screen scaling and things like that are a little bit better. You don't waste, extra space for, the browser pane and that type of thing. But either of those are available. So the first thing you have with the scope is you have your standard time base, and we can adjust that time base to whatever we want. We'll experiment that with a minute. And then you have triggers. And so like any scope, you have the ability of triggering from either channel 1 or channel 2, but this scope has a logic analyzer. It's mixed signal, so you can trigger from a logic analyzer edge if you want to as well. We'll just go to channel 1 right now. And then once then you'll have channel 1 and channel 2, and you'll have exactly what you'd expect for oscilloscope knobs. You have your volts per division, offset, and then it'll automatically calculate based on screen resolution what your sample rate is, combination of screen resolution and whatever the time base is set to. And so in addition to your scope channel 1 and channel 2, then you have your waveform generator. And the waveform generator has the ability of doing square waves, sine waves, triangular waves, and then you'll have a base frequency all the way up to 1 megahertz, and then amplitude all the way up to about 4 volts peak to peak. The next instrument is the logic analyzer, and we're going to go through each one of these. And I have up to 10 channels and turn the analyzer on. And last and certainly not least is the DC outputs. So these are 50 milliamps? Yeah, 50 milliamps per channel. You can go plus or minus 4 volts on those. So it's pretty cool. So you can just apply some power to your target. We're going to use that in this case as well. We're going to start out with the scope in a loopback mode. So we'll set up the waveform generator, and we'll set this to, I don't know, let's say 100 kilohertz, for example, and turn that waveform generator on, and we'll hit run. And so right now I'm just going to, hold on a second, I'm just going to turn channel 2 off. Yeah, we'll turn channel 2 off, and we'll hit run. And we can see that we're probably undersampling, but we can just start zooming in if we want to. And we can stop that, run, and you'll see exactly, and I can keep zooming in, and I can get all the way down to the sample rate if we want to. And so we'll start by just, we'll generate sine waves. It's like, we'll show some of the other capabilities with the WaveGen. We'll switch to a triangle wave if we want to. So you can see now we're generating a triangle wave. We could generate a square wave if we want to, and so forth. And so, so the WaveGen and the scope all run simultaneously, and just to verify that everything's working as we expect, let's show the FFT capability. So we'll flip to the FFT screen, and now you can see that the primary frequency is at 100 kilohertz, which is exactly what you'd expect. You can see the first spur is at exactly 3x that, and you'll see the magnitude is essentially 1/3. So you get 3 times the base frequency, 1/3 the magnitude. You see the next spur, next spur, next spur, and so forth. And just looking at the FFT, this should really impress you as to how good the noise floor is on this scope. Because this FFT is not messing with the data. It's taking the actual sample data, running a full FFT on it, and just displaying it. In addition to the FFT itself, you also have the ability to turn on, I must be out of screen space here. Let's go back here. Let me get rid of that. And we also have the ability to do basically what's called a math, real-time math. And I apologize for those of you in the back of the room. It might be a little bit difficult for you to see that. But what we have showing here is a real-time frequency. It's period, amplitude, max, min, and RMS. And those are all calculated in real time. And what's neat about that is, I'll just turn this off and we'll go all the way up to, say, a megahertz, which is the maximum frequency of the scope. Oops, hold on a sec. By the way, lowercase m is millihertz and capital M is megahertz.
By the way, it will generate down to 62 millihertz, which is a period of about once every 4 minutes.
And so if you really want to see the max capabilities, this gives you some idea. So we're generating a sine wave at 1 meg. Oh yeah, I'm sorry. And sorry about that. So we're generating a sine wave at 1 megahertz, and if we stop this, this gives you some idea. You'll see exactly 6 sample points, 1, 2, 3, 4, 5, 6. So it gives you some idea that we're doing 6.25 megasamples per second with a 1 megahertz source coming in. And so, and then we can also slide. Once we've stopped, we've got this huge buffer that we can take a look at the data. The buffer is up to 32 kilosamples total. It's a 64 kilosample DMA buffer, but the samples are 12 bits, and so it's basically 2 bytes per sample essentially, which is stored in that buffer. It's also interleaved. Keith will go into the details of that in a moment. So now, instead of measuring the waveform generator, so you can all see what the waveform generator is all about, let's start looking at real test points on our board. So this board is currently running, and we're powering it separately, and we'll take a look at the let's look at these 2 nodes. And so I've got to change my trigger point, which is to 50 millivolts, because obviously we have a much lower, and we'll hit run again. And now we'll go back down here, and this guy goes down here, and we will increase him. So, so now we're doing. Keith, if you go back to the previous slide, yeah. So right now we're actually looking at this node here, the LC tank circuit, and then we're also looking at the comparator output. And so, as an aside, as Keith pointed out, I received the alpha unit, unit number 1, and all the alpha the alpha waveforms live, and I had to go to special server and all that. And I committed to Keith that I was going to 100% debug this design with OpenScope. So I had an Agilent scope, $10,000 Agilent sitting on my bench, and I did not power it up. And
until you thought the OpenScope was broken.
Exactly. Well, and it's actually kind of funny. Like the op amp, wasn't getting enough bandwidth out of the op amp, and I was like, oh, OpenScope must be wrong. There's no way my circuit's wrong. And so I had to fire up the Agilent. My circuit was wrong. I discovered. So far OpenScope has been verified. So it gives you some idea what that looks like. And so now let's take a look at the FFT again, which is really kind of fun. And so we're actually mapping 2 FFTs on top of each other, which is kind of neat. So you'll have your DC offset. Now the orange trace, remember, is that, go back to here, the orange trace is this LC tank circuit. and that is actually biased at ground essentially. So that goes, plus and minus roughly 200 millivolts or so, because it's AC coupled from this node here. And then you'll see the DC offset for the square wave over here. And so you can actually see the effects of that. So, it gives you some idea. You can see there's basically no offset whatsoever on the orange trace here, at DC, which again gives you some idea of the quality of OpenScope. And then you see the primaries, and they perfectly align, although the square wave is, of course, at a little bit lower, is at a higher magnitude just because it's the comparator output that swings into 4 volts or so. But you can see, again, 1/3, 3x the base frequency at 1/3 the magnitude, and you can see that step through. Now, this is running at 400 kilohertz, roughly. And in fact, if we were curious what it was running at, we could actually put our cursor over here, and it will tell us 406.2, and we can verify that. Remember, I mentioned that they had all these CIPs that were basically doing all the calculations on the PIC side. So the PIC is actually outputting what it sees as the base frequency here, 407.5. The PIC oscillator is an RC oscillator, so you got to give it a little bit of a plus or minus a % or so, but they're pretty much spot on. And then this is the ADC peak voltage as well. And this is a metal detector. I think I mentioned that earlier.
Can you look at the math thing as well?
Well, the math, if I go back, and I'll be happy to do that. So if I go back to and that's a great point. So let me get rid of the FFT. We'll fire up the math. And again, I apologize for the folks in the back of the room because I can't make this any bigger. But if we compare the math right now, the math is showing, 406.4, and we're at, 407.5, and we're within 0.25%. And that's kind of expected because it's the internal RC oscillator, the PIC, that's doing all of its, baseline math calculations. So it's really, you can see it's pretty much spot on. And now we'll, just to show, hey, it's a metal detector, right? So let's throw some metal at this thing. And you can see the frequency went down to 395. You can also see that the peak voltage went from like 880 down to 817 because of eddy currents, essentially. And so we can see all that stuff correlate with each other, which is really kind of fun. So to your point, yep, you can show all the math in real time as well. And it's an oscilloscope, so first thing we did is I verified that the circuit was working exactly as expected and consistent between the OpenScope response and all my test points as well. And it's a scope, so we can take a look at all kinds of other test points on the circuit if we want to. We could look at the op-amp output. So this is I would take a look at this. This is essentially comparing the LC tank output versus the op-amp. We have roughly a 5.7 gain here. So these two scope channels are referenced at different points. And then if we want to, we could look at the peak voltage as well, which is, should be this node here. Let's see. Should be this node here. And so that's the peak detect voltage. And so that gives us some idea what the peak detect is. And we should see that peak detect voltage go down slightly as we introduce metal to it. So everybody can see the peak, you can see the peak voltage go down. Everybody can see that as we put metal towards it. And we can also see the primary LC tank amplitude go down. And we'll see its frequency change from, you see it's down to 392 and up to 406. As I mentioned, this is a mixed signal logic analyzer as well. So why don't we turn that node on as well? So we'll stop this thing and let's turn on logic analyzer channel 1 and analyzer 1. And I'm going to connect the logic analyzer. I'm going to have to unplug the serial UART here. And you can see that there was a bunch of UART data that was being sent. And so why don't we take a look at this at the same time? And so let's hit run. And we can see the actual data. And I might, hold on a sec. And let me zing this back.
While you're playing with that, you considered a viewer mode on this so we could all follow along, so we could just see what was going on without being able to change the controls?
That was considered for class unit. We actually, it's an advanced feature, and it is in the design, but it's not in the Yeah, sure, for classroom, absolutely.
Well, even not for classroom, but if I have something in my lab with my Wi-Fi anyway, and I put this over there, and just got a monitor here and one over here that are working.
Yeah.
It could be handy.
We've considered it, we just, you know, we haven't gotten there.
Yeah, just wondering. Good.
Absolutely. So, yeah, no, we're good, actually. Thank you. And so, so I'm going to wrap up so everybody can see the mixed signal. You know, you can see the logic analyzer output against our scope inputs. I didn't really zoom in and out of that, but it gives you some idea of the mixed signal capability. The last piece I want to show everyone is, so I should be wrapped up in a second, is we also have network analyzer capability. And so, so what we'll do here is we'll connect, and sometimes you're going to have to give me a second. I sometimes connect this incorrectly. So, so let me connect. That should be on this side, and scope channel 1. And
Oh, yes.
Keith, we got a question from the back row that I think would be just good to say. There's an adapter for the analog discovery 2 that lets you use some scope probes.
Yes.
Can that be used along with this?
Yes,
as well?
the BNC adapter, we pinned it out for the first 2 oscilloscope channels and 1 wavegen channel. We pinned out exactly the same as the analog discovery. You can use the BNC adapter with the scope probes. Works perfectly, except for wavegen 2, which we don't have on this board. So if you buy it, 3 of the 4 BNC connectors will work, and they work well. And it actually improves the quality of the signal. So yes.
the last demo, I only take a second, is anyone here ever do a network analysis, use a network analyzer? Believe it or not, that's built into OpenScope, which is truly amazing. So what I have here is a bandpass filter that I've just connected to OpenScope. Its center frequency is set around 10 kilohertz or so, and I connect the waveform generator output to the input of the bandpass filter, and then one is scope channel 1 to the output of the bandpass, and then it does an automatic sweep and plots it. And this is this can actually be a bandpass or it can be a high pass filter. So I'll disconnect this jumper here and we'll rerun it. And so this should be from a band pass. It should switch to a high pass now, hopefully. And we'll see exactly what it gives you some idea of what it's doing. And so you should see it, you know, level up at the top and exactly as is. So pretty impressive, huh? Any questions? Yep.
Protocol analyzer for the logic probes?
It has the hardware capabilities for it. In fact, I actually
projectors and stuff. Everything just went down.
That is not good.
Did you step on the power?
No.
Oh, there.
Really
Like
bad
just,
question?
like just came back.
Yeah.
Jeez.
Well, my laptop didn't.
It must have been partially, sorry about that.
Yeah.
It may have also killed your video recording.
Yeah. Anyway, where was I talking? What were we? What question was I answering?
Protocol, yeah.
I have 5-pin set for protocol analysis, all on port F, so you
I
can
don't know why this is not,
sniff. But I also PPS out UART, SPI, and
I don't know, why had that
I2RC
disconnected? It was
participate
like,
with the protocol.
I've got power down here.
But I didn't.
yeah, no, I think it's okay. I don't know.
And then,
This thing's flashing. I don't know what its issue is.
Hold it down and see if I-
Hardware upgrades required at some point, or is this hardware?
No, this hardware is all. It's all
On
there.
lamp auto.
John, man, it's too long ago.
Yeah, I think you're probably
We'll
right.
start using it. Yep. So this is giving me the stats like.
Yeah, I'm getting the same problem. I think it's because the lamps are hot, and so they want to cool down.
Okay, so
So we're having hand signals.
We are, yeah. So we go back, and might have been better. Maybe we just need a little fire and some of those old those old templates, that we sort of throw.
right. So while Giselle is figuring this out,
What is the voltage, input voltage range on this?
plus or minus 20 volts. Okay, and if you use the BNC adapter,
Not a lack of power.
because it's got a times 10 volt.
There we
I
go.
think I finally got it back. Okay, so I'm set now.
Happy to help.
Thank you.
Yes, the way the web pages are loaded, if you type in waveforms live in your browser, it'll come down from the Digilent servers. If you type in the IP address of the OpenScope will return a redirect page, which will take you to the Digilent servers. But if the Digilent servers aren't visible, like your mobile woods, and you don't have internet connectivity, and you have to use SD card plug-in with the pages, you'll then pull the pages off the OpenScope. So you can run totally safe. It's a little slow. It takes about a minute to load the pages off the OpenScope, which is why we always hit the Digilent servers first and do that. But it works.
If you're using the iOS app, does that?
You don't need to load the pages. That's the iOS app that's needed. All right, so what are the major components in the OpenScope? Obviously the hardware. And you know, we've got an RF24 radio for Wi-Fi. We obviously have serial. We use an FTDI chip for our serial. We've got some minimal analog circuitry. Obviously the fly wires, but you can get the VNC adapter if you want. And of course the major component, the thing that does all the work, is PIC32MZ. The firmware, of course, is a big component of this. And this product, the firmware and the hardware, were designed together from day one. I am fundamentally a software engineer. I worked for years at Microsoft, worked at Windows, came to Digilent, didn't know anything about hardware. And so this design is really an OpenScope designed by a software engineer. So from the get-go, firmware was the name of the game. And with that came a lot of calibration. That way I can use cheap components. I'm not really particularly a guru in analog circuitry, so everything I had to do had to be simple, and I just corrected for it in firmware. Communication, there's Wi-Fi, USB, and then of course we have storage. We have an SD card for storage and a 0.5 megabyte of RAM. Waveforms Live is technically a TypeScript program, superset JavaScript. It just communicates to the OpenScope via post commands with JSON, with a JSON body, text body, and it gets a text response. We also do what's called chunked responses for the binary data, chunk transfer encoding, so standard encoding, and that all goes through the HTTP protocol. And then we have, when we want to connect through to the OpenScope through the USB, we have, it's actually a local server. It looks just like the OpenScope server, but it locally runs on your PC, and it translates the HTTP calls into serial calls, and then runs it over the serial line to the OpenScope, and that's how the Digilent agent works. We needed this. It started out as a configuration utility to get your Wi-Fi parameters on the OpenScope, and we said, well, if we're going to do it to get the Wi-Fi parameters on there, we might as well do it for everything. So we just allowed that path to be identical to the hosting communication. And of course, the only difference is we can program the Wi-Fi parameters through the serial card. Yes?
Can you collect data through a CSV or something? It's like on CSV or logs or what?
Right now we're doing what's called a data logger for those little stretch goals, and I'm working on that right now. It's going to have true data logging, and I'll put it on the SD card, and then Waveforms Live will be able to read that file and get the data logs back.
So can it read a file now, or is that coming with
Shh, it reads a file now. But we're not advertising. You won't see that in today's lecture. But yes, that's working. File commands to JSON are now working. So this is the block diagram. I apologize, you can't see it. I know that. The reason why I put this up is this is the thing that I started out with a year and a half ago. This is how I was laying out the resources. It's got all the pins in it. It's got the resources I used internal to the MZ. And it was a block diagram of the analog circuitry. We got, in the analog circuitry, we got a fixed divided by 5. We got a 4-gain input stage, goes right into the ADCs. This is our PWM circuits. This is how we get our DC outs. This is our waveform generator. What we do is we go to an R2R ladder and got some offset, an op amp that we can do some offset and it goes out. This is our reference, our 3-volt reference going in. These are all the internal pin layouts. So I know you can't see it. Keith Chamberlain decided to make it more visible for us. So he did that for us. So the first thing when I laid out the OpenScope is I had 2 oscilloscopes, a wavegen, 2 DC outs, a logic analyzer, and I had to lay out the resources in the MZ to do all this. And I also had to lay out the pins. I had to make sure I mapped all the pins to the right place. And this was a highly iterative process. And here are some of the things. I use 9 of the 9 PWMs. I use 7 of the 9 timers. I use 5 of the 5 interrupts. I use 3 of the 6 SPIs, 2 of the 6 UARTs, 1 I2C for your protocol analysis, which we haven't implemented. The funny thing here is I use 9 of the 8 DMAs. I had to share one because I ran out. I use 4 of the 5 dedicated ADCs, 8 of the 43 shared ADCs, 2 digital compares. This was for our trigger sensing, and one digital filter with the logging, with the data logging we're coming in. I use 3 digital filters, and I also use 14 of the 8 DMAs. Well, you got to do what you got to do. So the PWMs is how I get offset control. I mean, with a PWM, it's a duty cycled square wave. You put that into a low pass filter, you get a proportional DC voltage out. And so all when I do offset setting of the input signals or the function generator, I use the PWMs to generate that. Also the DC out, this is exactly how the DC out works. Generate a PWM signal, I filter it, I put it in an op amp, there's your output. And so those are how the PWMs are used. Now, the downside of that is they're slow. In the software, I refer to that as setup time. In circuitry, it's your time constants on the filters. So whenever I switch a PWM value, I gotta wait. I gotta wait for it to settle. So all of the instrumentations are slow when you change the parameters. I gotta wait for everything to settle before I turn them on. But we use the PWMs for our offset control. The timers are all used as triggers. That could be triggering the DMAs, could be triggering the ADCs. It could actually be telling you when to stop taking a collection of data. So the timers are all triggers. The DMAs do all of my data transfer. So when I'm collecting data in the ADCs, ADC completion event triggers a DMA, which puts it in memory. When I'm looking at the UART, and a byte comes in, the DMA is triggered, put it in memory. WaveGen, I use the DMA to actually push the pattern out to the port. So the DMAs are heavily used, and in fact, when the instruments are running, no matter how many instruments I'm running, it's just sitting there, instruments running, there's no CPU utilization. Everything's done in the peripherals. And yet, I'm collecting data, I'm pushing out the WaveGen, and that's why I can run all the instruments concurrently, because there's no CPU utilization. How are the ADCs partitioned? The MZ has 6 actual ADCs, hardware. 5 of them are dedicated, and 1 is shared. Now, you might think, well, you could use the shared one as a dedicated, but you can't because there's a lot of circuitry in there to make it shared, and it kind of screws up the timing. So if you're going to interleave, use 2 ADCs to make one faster one, you can't use the shared one. You have to use the dedicated ones. I use 4 of the 5 dedicated ones. I use two ADCs to create 1 channel, and I've got 2 channels, so I'm using 4 of them there. And then I use the 5th ADC to actually read feedback for calibration. And the calibration is very slow, but I get good data, and I can use the shared ADCs. So one dedicated ADC is not used. PWMs, we talked about those, and the timers we talked about, and this is just the allocation of what I actually used and where they're used. The DMAs, I use 2 DMAs on communication to the UART, 1 coming in and going out. I use 4 DMAs on the scopes, 1 DMA on the function generator, 1 DMA on the logic analyzer, and if you count it up, I use 9. So, I don't get it. SPI, I use 1 to talk to the MR24 radio. I use 1 to talk to the SD card. I have 1 to go to the protocol analysis, which we don't implement any protocol analysis. And then external interrupts, we can daisy chain this thing with other OpenScopes not implemented yet, but the hardware is there, so that we can trigger, when 1 triggers, it can trigger another. So let's start with the most simple instrument, DC outputs. Remember, it's just PWM filtered, right? We put it in line, I have a PWM signal coming out, I filter it, it's proportional to the duty cycle, and I amplify that using my voltage. Simple, right? a little block diagram of our PWM circuits doing that. Before I get going, everything in the OpenScope, I'm not smart, not a great analog guy, so I had to think simple. And we started out with our simple op-amps course. And this is very critical. If you want to understand how the hardware works in the OpenScope, you have to understand the next 3 slides. So we'll start out real easy. Remember this circuit, if you went to EE classes, this is your simple inverting op-amp. It's the feedback over the input resistor minus and times the input, and that gets the output voltage. Very simple equation, simple op-amp circuit. What I've got there is I got the AC input. Let's imagine that this is one of our analog input channels. That's the input analog input channel. Great. So now, same thing, nothing different, except this is a PWM. This is a filtered PWM, so we'll consider this as an analog, DC signal. And same equation, same thing. We know that, simple. And as I change the PWM value, the output will change. And then this is bias control. It's the same equation, same thing, except here I got some constant fixed thing. And what I can do here is, depending on what the bias resistor is I can adjust where the sort of DC state of the op-amp is. This is the real deal. Let's put them all together. If you remember simple op-amps, all of these just is the sum of that. And this is the fundamental circuitry of everything that's in the OpenScope. All of the circuits work this way. I have some constant bias control to set my DC output of the thing. I have some PWM offset control, which will adjust where the output of this will go from programmatically. And then in the case of I have an AC signal, I will then amplify or do whatever with the AC signal. In the case of the DC outs, I have no AC signal, so these two are the only ones used for the DC out. And this equation becomes very important of how calibration works, how all the circuitry works. I'm going to add one little twist. It's going to look ugly, but it's not. I don't tie this to ground in many cases. I don't tie it. See, the PIC runs 0 to 3.3 volts. And I got a 3-volt reference on it. So really my signal is 0 to 3 volts is my AC signal. And the center of that is at 1.5 volts. So my virtual ground isn't ground, it's 1.5 volts. So in many of the circuits, I have a 1.5 reference going in there. Well, that adjusts our equation just by offsetting stuff by the reference. It looks really ugly, but it's not. It's just the reference. But this is what you take away. That's a polynomial. The output voltage is some gain on the AC input, some gain on the PWM, and some constant. All the circuits are going to be represented by a polynomial. And what I'm going to do is I'm going to calculate what these coefficients are based on the resistors used. I will have what an ideal value is, but when I calibrate, I'm going to calculate what they actually are in calibration. Not what they should be, but what they actually are. And they'll be slightly different. But once I calibrate and I get that equation, the circuits run very nicely and accurately. So let's look at the DC output circuit. It doesn't look like that simple circuit quite, but it is. Here's my PWM input. Oh, you see the back of it. Here's my PWM input. Here's my feedback resistor. That's a gain of 4. Okay, gain of -4. Got it. The reason why is that my PWM has a dynamic range of 2.5 volts. And I want to have a dynamic range out here of 10 volts. So that's gain of 4. Okay. Where's the gain of 4 there? 12 over 3. Gain of 4, it's minus, but so that's pretty okay. I see that. I got some extra stuff in here. Remember, I said the PWM is coming out of the PIC. It's a duty cycle square wave. I got to filter that. This is 34 hertz, very low frequency filter. That's going to filter that PWM signal to an AC signal. But I got 2 of them. Is that because I want a 2-pole filter? No, it's not because I want a 2-pole. 1-pole filter would work fine. What happens is, if I route a square wave through my analog circuitry, I get noise in my analog circuit. I don't want noise in my analog circuit. But if I route DC through my analog circuit, I don't get noise. So I put this filter really close to the PIC, get it to be a DC signal. I route this around the PCB, and then this is just a noise filter right before I go into the audio. So that one's close to the audio. Now I'm routing DC through my analog circuitry, I'm not getting the noise. So that's why, and you'll see this all over. You'll see this dual filter technique on almost all of my PWM circuits. One close to the PIC, one close to the target. Now, this is at bias control. I mean, this is going to run between 0.5 volts and 3 volts. We'll talk about that in a minute. But this runs -5 to +5. Well, if I take halfway between 0.5 and 3, that's 1.75 volts. What I want is, if I got 1.75 volts here, I want 0 volts here. And I control that with the bias circuit. I just shift that. With that circuit, I shift that down to 0. And that's how I calculate these resistors, is if I put 1.7 volts there, I want 0 here, calculate those resistors and do it. Notice, even though this is a reference, it's a DC voltage, I put a filter on it right next to the audio. Anything I pick up along the way in the routing of the PCB, I'm going to kill it. This is because my ADC on the PIC is 0 to 3 volts, and the center point is 1.5 volts. So that's my virtual ground. 1.5 volts is my virtual ground for the circuit. Okay, there it is. And lo and behold, I put a filter on that as well, right next to the audio. So I'm filtering everything as it gets close to the audio, create stability. Now, I'm going to calibrate this thing. This is going out to the output pin. This is your DC out. Internally, I connect that to a feedback calibration circuit. And of course, I'm going to read that back into the ADC. I got to shift that back up to 0 to 3 volts. Well, I got a little reference here and some diodes and stuff like that. And, I mean, resistors and whatnot. And I'll shift that up. So if I run plus minus 5 volts here, I'll get 0 to 3 volts out of here. And lo and behold, there's that filter again. Filter. Keep it filtered everywhere. These resistors have to be precise, because whatever this voltage is that goes into the ADC, I have to have an accurate answer. And the only way I can do that is if I have very precise resistors, at least 0.1% resistors. So all the feedback circuits are designed 0.1% resistors. They're all passive. No active components in them. So I can get good, clean feedback voltages into the ADC. Sort of an overview of the whole thing. My PWM offset, my bias control. This is my summing node for the op amp of these two things, the output, and then the calibration. Again, all of the circuits are designed like this. Because I like to make my life easy, I have to pick some kind of PWM frequency, I have to pick some value for it. The PIC runs at 3.3 volts. If I create the PWM to have 330 individual steps, that means that each step is 10 millivolts. I can pick that in my brain pretty easily. So there's 330 unique values in the PWM in the duty cycle. It runs, the peripheral bus runs at 100 megahertz. I divide that by 330. My PWM runs running at 303 kilohertz. This is both good and bad. It's right in the middle of my analog frequency. That means if I route PWM anywhere in the analog, it's going to be picked up and not filtered out. The analog frequency cuts off at about 3 megahertz, so it's all designed to filter out at. That's going to be noisy. That's why you see all those filters everywhere. I don't want to route that through. It turns out, as you notice from the FFTs that John was showing you, in particular in the loopback circuit from the wave gen, was nothing at 303 kilohertz. I got it. I killed it. I was worried. Because everything is calibrated, I need headroom on the top and the bottom. So I'm not going to run the PWM from 0 to 330. Sorry, 330. I'm gonna give myself some calibration room on it. So I run it from 50, which is 0.5 volts, to 300, which is 3 volts. This gives me 30 above, 50 below, to calibrate out should the components that are laid down are wrong and my coefficients. So even though I design it so that, 50 gives me whatever the output is, or in this case, 1.75 is supposed to give me 0 on the output. It could be that 1.74 gives me 0 on the output, but when I calibrate, the equations will tell me that. But I need that a little headroom on the top and the bottom for that calibration. And I gave plenty of headroom. But what that means is my PWM voltage swing is 2.5 volts. And I do this everywhere for all the circuits. Why? Because I don't want to have too many different variables in the system. But I could have shifted it for various things. But I just made this constant. The other advantage is I can run all the PWMs at the same time with the same interval, which was convenient because it saved resources. So where do I use the PWMs? That generates the 2 DC outs. It goes and does the 2 offset inputs for the analog ins, and it's used also for the function generator offset. So that's what 5 of the 9 PWMs are used. 2 are put through the protocol analysis, and 2 are actually used in interleaving the ADCs. So that's my 9 PWMs used. As I said before, there are at least 2 filters on every PWM, not because I want 2 poles, but because I want DC coming away from that PIC, and I want to filter it at the target pocket. And again, the setup time, depending on the filters, is somewhere between 30 and 100 milliseconds. But I actually in the software gave it 500 time constants, so I'm definitely stable at the when I turn on the instrument. That, by the way, is about a half a second. So whenever you change the PWM, everything stalls for about a half a second. In human sense, you don't see this. I mean, you click the button, and things happen. By the time things happen, it's stable. Yes?
Can you remind me the analog input voltage range?
Plus minus 20 volts. Okay, so I said everything, all circuits are done this way, which means I can describe all circuits as polynomials. Here they are. The feedback circuit, I gotta trust because of those 0.1% resistors. That's the equation. DC out, that's the equation. Analog input, and I have some resistors here that I didn't put in because there are 4 stages in it. When you plug in the values of the resistor, you get 4 stages. And the waveform generator. Now this is the ideal waveform generator equation. This is the 10-bit DAC value coming out of the port H. This is the PWM value, this is the offset. And that'll give me the microvolts of the output of the function generator. But we do the function generator a little different. The only thing I actually do in the equation is the offset method. The actual value, the DAC value, I do through a lookup table, and we'll describe why I use the lookup table and why that's so important. We'll do that in the waveform generator part. This is kind of you just got to understand, this is my feedback circuit. 0.1% resistor is the equation. I have to trust it. Just to give you an idea, if the voltage here is -5, I get a DAC value of 34, which relates to 0.0252 volts going into the ADC. If I have a value here of 0, I get very close to 1.5 volts. If I have a value of 5, I get 3 volts out here. And so this is how I do calibration. This equation is baked in. However, this voltage is not. I actually measure that. But this equation is baked in, and when I do calibration, I read those values. I use this equation to determine what the voltage is that's coming in, and then I can calibrate all of the instruments. So this is the sort of the math on the DC out. This is what the equation is. Remember that the DC outs doesn't have any AC signals. It's just the PWM and the constant. I put the PWM value 50 to 300 in here. Actually, we're not doing that. So PWM value here. This will be what the output of it is. Now this, of course, is ideal. This is not calibrated. Calibrated, these numbers are, this number and this number are going to move around a little bit. how do I calibrate? Simple linear math. What I do is I apply what a PWM voltage to the output, and I think I know what the output voltage would be, but I read the feedback and I get what the actual value is. Well, you remember all linear math, 2 equations, 2 unknowns? I do this twice. I do it high, do it low, take the difference, do a little math, and I can calculate what the first coefficient is, and then using one of the points I can calculate what the second coefficient is. And the numbers I get back are approximately that, and they are approximately that. They're not exactly that. But once I've done that to the circuit, I've characterized the actual physical circuit on the board. Of course, every board is different because the resistors way down are also different. So what has to be precise? We talked about calibration, we talked about feedback circuit being precise. What do I actually have to do to be precise, and what can I be sloppy on? The most critical component on the board is the 3-volt reference. It has to be 3 volts. I spent the most amount of money on that component. I made sure I got a good one. The ADCs, I've got to trust the ADCs on pick 32. I can't do anything about it. I have to trust them. And the feedback circuits, I have to trust them too, because that's using calibration. So I use 0.1% resistors on the feedback circuits. How did I do the design? Here's my reference. Got a big capacitor here, 10 microfarads. Filter that baby down, but it's a straight line right into the ADC. There's no substantial load on this. The only other load are the inputs to these voltage follower opioids. Highly filtered. Actually, Ajay told me exactly what capacitors to put there to make the MZ work the best. And I followed that and it worked out well. But highly filtered, very closely placed. This is placed very close to the MZ, so it'll pick up noise. I have to trust that. That is the most important. Then I put these through voltage followers, and these are the references that go around the board. Well, wait a minute, I put it through a voltage follower. It might not be 3 volts, it might not be 1.5 volts, and that's absolutely correct. It might not be 3, it might not be, and it's not, it's close. I actually put those into the ADC, and I measure what they are. Wherever I have a 3 volt reference or a 1.5 volt reference, I actually use what I actually read back in the ADCs for those voltages and put that in as part of the equation. This typically is coming up very close to a microvolt of 3 volts. And this is usually within a microvolt of 2 to 1.5 volts. So the followers are actually pretty good. Yeah.
So the VREF plus going into the ADC, that's a 3.3 volts, not a 3?
Yeah. See this here? 3 volts.
Yeah.
3 volts. This signal is the same as that. It's just
Yeah, I just thought you had said earlier you were using the 3 volts into the VREF. So
yeah, it is 3. It's 3 volts into the reference. The PIC runs at 3.3 volts. The power supply in the PIC is 3.3. The reference is 3. Think about it. I don't want that SAR going up against the maximum voltage of the PIC.
But so you've got VCC 3.3 volts. That's going straight into your VREF, isn't it?
This is 3V0.
No, I think what is
The Zener is
so if you look at the 56 and 35 and 136, then you can see.
No, this is 3.0. It's
Okay.
3.0.
So the Zener or reference diode?
It's a reference diode. It's drawn as a Zener, but it's a reference diode. It's an actual, that part is what it's designed to do, is to be a reference.
Okay, so you're using the 3.3 to supply the current.
Yes, but there's a resistor here.
56.
Yeah, there's a resistor here, and then it goes in here, and this clamps it to 3
Yeah,
volts.
I wasn't seeing the reference part of it.
Right, yeah. That's the...
Very schematic.
Keith, could you explain maybe why you have those other series resistors from that reference before feeding the unity gain?
I need Ajay here to really do a good job here. Let's say I get noise right here. I pick up noise. Looking this way, I got a filter. Looking this way, I got a filter. Okay, if I only have one resistor, I don't get that filter on both directions.
Cool.
Okay?
It's clever.
Yeah.
So But your center area is the part where you have, there's a lot of pieces.
This will be close here. This is all close to here. And then this is routed a little bit, and then this is close to these. Okay? And of course, you would say, well, on this one, you know, you don't need resistors at all. But you do if you want the filter to work. So, again, filters were the name of the game on this circuit because this is a digital circuit on a 6-layer digital board. I'm trying to do analog. So, filters are everywhere. As design goes, anything that didn't need to be precise, which is just about everything, I designed as if I used 5% resistors. I actually put down 1% resistors because they were effectively no cost difference. But I designed it as if I was using 5% resistors. Likewise, I designed it with 20% capacitors, but I actually put down 10% capacitors. Now, capacitors were, those are just some frequency adjustment stuff. They could be pretty sloppy, and capacitors aren't really playing into this very much. But I still put down 10% capacitors. Again, cost difference was insignificant. Yes?
What was the order of your
The order of the 6 layers on the board was signal, ground, power, ground, signal, and there was another signal layer, I don't know which where it was. It might have been between the second power and ground. There were a couple of the power plane was kind of split up because I got 5 volts, I got 3.3 volts, and so that plane was kind of split up a little bit. I would have to actually go look. My layout engineer did that, and we have a very good layout engineer. I think that's the one.
By the way, are the circuit designs also on GitHub? Is that downloadable?
Nope. We've had 4 of our products ripped off, so we're not going to publish the projects. This is just too much IP to let some Chinese company rip off. So the voltages that are route around the board, the 3 and the 1.5, I actually don't depend on them being 3 and 1.5. I measure them and I use them in the math. The only place I have to depend on it being 3 is what's going into the reference of the MZ. And the other thing I depend on is the op amps behaving linear. And this is not slam dunk. Op amps don't behave linear, and we'll go over all the things that op amps don't do well. Okay? Common mode input is one of, especially on an inexpensive op amp, is one of the biggest problems. I got sort of like a simplified view of the input of an op amp. It's not probably actually how, this is bipolar. It's probably not actually how it's done, but it's sort of like the one you'll learn in school. But it gives you the idea. It takes a differential of these 2 voltages, and the output will be up here. And then you go into an amplifier, the gain amplifier. But the thing is if you notice that it's a bipolar one, there's at least 0.7 volts here. So the common mode certainly can't go above, VCC minus 0.7. You get up in there and these diodes don't behave linearly anymore. So what happens on a lot of, especially inexpensive op amps, is that you've got a maximum common mode voltage that's VCC minus something. And they're typically 1.2 volts or 1.3 volts, and that's probably because they want to get down off of it. They might have two diodes in there. I don't know exactly how they're implemented. But that's where the common mode input voltage has to be so much lower than VCC. And unless you buy a rail-to-rail input one, they're not more, rail-to-rail's more expensive. I want to use cheap ones. So I use most of my op amps in an inverting mode because the inputs of the op amps are around 1.5 volts. Well, if I got 3.3 volts driving my op amps and I subtract 1.3 volts at 2 volts, 1.5 is still under that common mode range. So I can use a cheap op amp. And they work very linearly in like VCC over 2. That's the best linear operation of the op amp. So that's one consideration. I'm going to use that op amp and inverting for the most part. I don't have to use a rail-to-rail now, so that helps out. Another problem is called something called input bias current. If it's a bipolar op-amp, in order to turn this transistor on, current's got to come out. And indeed, the op-amp I use in the front end, there's quite a bit of current that comes out. And that affects the offset of the op-amp, and you've got to compensate for that. If you keep that common mode constant, like you do in an inverting op-amp, that value is constant. And you can compensate that as a constant. My little bias control that I put in, you just tweak that, take that out. If I'm running in a non-inverting mode and that bias is, common mode's doing this, that bias current's changing, and that's a nonlinearity. I can't deal with it. So I use it in the inverting mode. So you'll see me use these for the AC signals in the inverting mode. Clearly, if you approach any of the limits, input or output, you're going to start getting nonlinearities because you can't sink or source the current anymore. You're getting too close to the rails and things happen. So you want to keep them away from the rails. Output consideration. You know, you can't, it says it's rail to rail, but if you get close to the VCC or the VDD, you're going to be 20 millivolts off. It's as close as you'll get. And then, of course, your headroom requirements go through the roof. Sure, you can go very close, but you can only pump 1 milliamp. If you try to pump 10 milliamps, you can't get close. You've got to be further away. That's called headroom. And headroom is a problem. For example, on my 3-volt reference, I'm running my op-amp in it as a follower. And I only have 300 millivolts of headroom, but I need 8 milliamps coming out of that op-amp. It turned out I originally put the microchip part down, and I needed 400 millivolts to get 8 milliamps out, so I couldn't use it. And I had to go find a very specific op-amp that had that headroom in order to do that. Now, the only time I use non-inverting mode is for DC signals, PWMs, and the references. And that's because they're used at a very constant voltage, and everything's still, the bias current's constant, and I can measure it. It's constant. So that's the only time I use them in voltage tolerant. So that's basically what I say here. Use inverting mode for all the AC signals. I can use non-inverting mode for the DC signals. This is an ST part. It's the only one I could find. It turned out it was very expensive. I was very happy to find it. But I traded bandwidth. But these are DC signals. I don't need bandwidth. So I traded the cost of really low bandwidth for the head. That's like 15-cent part, so it's really very cheap. Okay, let's go on to the analog inputs. Now this is going to look ugly on the circuitry, but remember that simple circuit. It is still that simple circuit. It's just got a lot of filters and junk around it. This is the divide by 5, first op-amp. This is bias, reference, PWM, and recipient. There's our three components coming in. And this is the summing node of the second op-amp. This is my gain select. It's an analog mux. It's just the feedback resistor going to this op-amp. This is PWM select. So I can change the way my PWM is scaled based on the feedback resistor. So this is just PWM. And this is the analog input. This is where I had problems with input bias current. If I look here, I have 200, this is a 1 megohm resistor. Don't like big resistors on digital boards and analog circuits. They just suck up noise. But we have to have a 1 megohm input impedance. So there it is, 1 megohm. This is a divide by 5. That's 200K. Well, I got a little input bias current coming out. This thing drops about 70 milliamps when this is 70 millivolts when this is 0. I had to take that out with this bias control. This is my bias control. I had to take that out there. But because I'm running this inverted, this common mode is constant, bias current is constant, I can take it out. This is a very inexpensive op-amp, 23 cents. But since I'm running in the inverting mode, I can get away with it. Over here, Same kind of thing, this is my 1.5 reference, because that's what the ADC wants to see at the ADC. And I can switch through this analog mux. Notice that I run the analog mux at 1.5, constant. Why? If I run this analog mux at the varying voltage, R on changes. I don't want R on change. This is a constant R on at voltage. So once I calibrate, it's not going to move. It's not going to give me nonlinearities in the circuit. It's going to stay put. So I run this at 1.5 volts all the time. It's in the feedback. Right there. Sure, this is going to go all over the place. These resistors are going to drop the voltage to match the current coming into the op-amp. So, stage 1, divide by 5 gain. This is how I can go plus or minus 20 volts. This is going plus or minus 20 volts. This is swinging plus or minus 4 volts. That's my plus or minus USB. Something that I didn't say, I run directly off USB voltage. USB voltage can be as low as 4.5 volts. It doesn't have to be 5, it's usually not. And I have a charge pump giving me my minus USB voltage, which limits me to 100 milliamps on the minus side. So I try very hard to use the minus USB as little as possible, because I want 50 milliamps of that to be able to drive the minus DC out. So I really only have 50 milliamps of the minus side that I can use in an op-amp. So my design is to get the op-amp shifted up to a reference of 1.5 as fast as I can, so I can run 3.3 to 0 on the op-amps. Obviously, this one I have to run plus or minus USB, I just have to do it. But this one I do not. This one I run 3.3, because I shifted that. And so let's go on with the circuit. So there we are, plus or minus 4 volts max. This is actually bias control for the second stage. It's drawn funny. This is also going to shift me up to 1.5 volts here. This is actually the summing node for this op-amp, even though it's kind of drawn, here. This whole node is the summing node for the second op-amp. This gives me the summing node is going to give me bias control, AC input, and PWM. These are my feedback resistors and gain select. As I switch the mux, I get different feedback resistors on this, which changes my gain. Over here, when I change my gain, I got to change my PWM resistors, so I switch those also. We'll talk about specifically what that offset control. I want you to notice that there's no capacitors. It's DC coupled the whole way. I want to do that because I want to use cheap components. I don't want to have to do any kind of AC compensation. I don't want to have an AC-DC switch. I don't want any of that kind of crap. This is DC coupled all the way. What we do here with PWM is we can shift what the voltage is. So if I have a 3 volt peak-to-peak volts that's centered around 15 volts, I can still center that at 1.5 volts going into the ADC by changing my offset control. I can literally pull that voltage down so I can read that 3 volt peak-to-peak going into that. So I can still have a gain of 1, but I can shift it down. Yes?
You're powering off the USB. Do you have isolation?
Nope. I've depended on the power rejection of the op-amps. Power rejection ratios. Yep, nope. There's only, there's an LDO that goes from USB plus to 3.3. That's the only, and then there's a charge pump to get from minus USB. That's all there is. So, yep.
I've fried a computer once or twice.
Very powerful, nice strong DC with the Wi-Fi.
Or you just power up your battery, yeah.
Clearly, no matter what I do with this plus or minus coming in, whatever my gain selected, my gains have, I have 4 gains. Unity gain, which will give me 3 volts peak to peak. Divide by 4, so I get 12 volts peak to peak. Divide by 8, 24 volts peak to peak. And then 340 is 40 volts peak to peak. And then I've adjusted the PWM so I can adjust that peak to peak. So, you know, if it's like 3 volts peak to peak, this will then adjust from 18 volts, 18.5 volts to minus 18.5 volts will be what I can adjust it. So if my 3 volt peak to peak is at the very top of my 20 volt range, I can still shift that down so I can read it into the MZ. Or if it's at minus 18.5 or 20.5 volts peak, you know, half of 3 volts peak to peak, you get to minus 20, I can read that in. But as I go through the various gain settings, I adjust that so I get the full idea of range. And of course, at 3/40th gain, I don't need any offset control because 3/40th gives me the full 20 volt range. And so that's why that's just a 10K resistor up there. It's just something big. So this is what we call pseudo AC coupling. You just set your offset, and then you can shift your voltage and get kind of that pseudo AC coupling. And it allows me to run a complete DC circuit because I really don't want a capacitor in my AC signal or my DC signal because I got to compensate for that. The moment I put a capacitor in, I got to start compensating. And I'm not that smart, so I can't really see. What is the frequency response of the analog circuit? This is not going in, this is at the ADC pin on the PIC. It's not what the PIC's doing. It's just the input pin to the PIC. What is the frequency response? The worst case is you need a gate. My 3 dB point is 2.9 megahertz. It drops off very quickly. At the 1 megahertz point, I'm plus or minus, I'm less than 0.5 dB plus or minus at the 1 megahertz point. It's pretty flat. That's what you get when you use no AC coupling. You can do this. The easiest one to do is the maximum attenuation. 3.5 megahertz is my minus 3 dB point, and you can see, again, this is a half a dB each division. You can see it's just flat. It drops off sharply, obviously, once I exceed 1 megahertz. And that isn't just because I've got filters in the circuit, that is because the op-amps are proven out. I mean, I got the cheapest op-amps I can buy that can still do the job. And so a lot of that is the op-amps proven out. Which actually helps you, because when you get high frequency noise, the filters take it out and the op-amps take it out. It doesn't make it in. And so that actually helps you. That's one of the nice things about having a 1 megahertz scope. It's pretty easy to get rid of high frequency noise because almost everything's greater than megahertz. So it worked out well. Okay, so there's the equations, the mathematical equations for the analog in. It's described as a polynomial. And for the various gain settings, these are what the mathematical values would be given the resistors that are on the board. Of course, that's not what actually happens. So I have to do the same calibration trick. What I do is I take the DC out, and I put it on the analog in, and I actually calibrate the DC first, but I don't depend on the DC voltage equation. What I do is I drive the DC out, and I actually read the DC output's feedback circuit to see what the voltage actually is. And then I take that DC out and I put it into the analog in. That's why in calibration you've got to tie the DC out to the analog in. And I can run the input stimulus to the circuit. And, you know, 2 equations, 2 unknowns, 3 equations, 3 unknowns, so 2 equations. But first I run the DC to get the 1 parameter, then I run the PWM to get the 2nd parameter, then you can calculate the 3rd. And this is the final equation that I use internally, and I calculate these coefficients. Yes?
How often do you have to run the calibration?
Often as you want.
Like how many minimum, like?
I typically, you know, in room temperature, I'm finding it doesn't work. I calibrate it once and it works at room temperature.
Is it calibrated from the factory?
It is calibrated from the factory, except because the firmware has changed so much, you're probably not going to calibrate because we changed the firmware. I got better at the calibration.
Okay. So if it updates firmware, it knows and says, oh, this version needs new calibration.
In fact, even if you somehow scrambled it by using MPLAB X to program it, the calibration data won't be in the flash, and it'll tell you to calibrate. Yeah, so it knows it's not been calibrated. It tells you, it forces you to calibrate. And it gives you the instructions on how to do it too. It says put the, the yellow wire to the red wire and the blue wire to the white wire, and then run calibration. It takes about 30 seconds to calibrate. And it calibrates the whole instrument. So if you are going to use it hot or cold, I would suggest recalibrate, because we make no assurances about the temperature of what's going on. It's calibrated room temperature. You use it at room temperature, it's pretty good. But if you're going to go outside in sub-zero weather or something, I recalibrate. Take the 30 seconds and recalibrate.
So the injecting of your reference level is external to its user. You put a jumper or something there. Is that what you're saying?
No, you actually use the DC out to inject.
Yes, but it's routed externally.
Yes, you actually literally have to plug the wire.
Okay, so if you had a reference of known accuracy, you could use another reference?
No, because I actually because I have to do the two equations to a known thing. I have to drive it at one value and then drive it at another value and take the difference. So one single reference wouldn't do it for me. And I'd have to know what those values were. So I actually just drive it, do it for you. And I have to do multiple points, right, to get that. So it actually works out very good. I mean, I had a guy that he wanted to actually put this on like a $10,000 scope to qualify how good it was. And I'm like, yeah, then I'm not going to sleep at night. Because it might not be perfect, but it's actually pretty good. The calibration that you get back is a very good scope. You get very good numbers. And if you use the BNC adapter with the probes, you get really good numbers. Okay, so the calibration actually works. Of course, the temperature changes, all bets are off. Any other questions? So the question is, this is your pop quiz. Before calibration and after calibration, what's the difference? If I were to use the circuit uncalibrated, how far off would it be? Would it just be 1% off, or would it be like 50% off? I'm using cheap components. What do you think the difference is between, anybody got an idea? You say 3%, what do you say?
5%.
5%? 10? 1? All over the map. How did I know? You want to know what? I didn't know either. I had no idea. I said, what's going to go? Now, this was a prototype, which means I was working on this thing. 0.27%, 0.49. This is the difference between uncalibrated and calibrated. What does this tell me? One, it tells
based on one unit, right?
This was based on one unit. Now, I'll give you the cross unit number, okay? This is based on one unit. And this was based on the unit that I was working with, okay? So I was actually tweaking the values of the resistors for production. So tweaking was actually for this unit too. So this is good. Without a doubt, this is good, right? There's no number there greater than 1%. Okay? What did that tell me? My equations were right. I was running the op-amps linearly. I was definitely in the zone with 1% resistors. I definitely had headroom for calibration. This, by the way, totally stunned me. I really thought it was going to be greater than 5%. I thought it was going to be more like 10%. And all through the design, I was totally prepared for 10% variations. I ended up with this, and I was just like, I had to run in Clint Cole's office and say, block. I mean, it was great. The real answer is 3%. And I actually, when you calibrate, I will print out those numbers for you in the calibration. I will show them to you. You can look to see how it is. I print it out. And when you do it on Waveform slides, you can see it. You scroll through all the numbers. And 3% is what is the max. It's usually about 1%. There's a couple of offsets, and particularly in the 340 scaling setting. And the reason for that one being off the most is because that input bias current, I can't control, from part to part, that input bias current on that first stage just kind of wanders all over the place with manufacturing. And that changes the constant of, and it's most effective in that 340 scaling. And that's the one that wanders around the most. And that one will get up to 2.9% or so.
the tolerance on your reference file?
25 parts per million. Yeah, it's pretty good. I could have got 50, but I went with 20. Because that would have to be right. Okay, so we're about here at DMA process, and we've gone over a lot of the hard stuff. All right, I'd like to take a little quick break. I'm sure we all need it. I need to drink water. So when we come back here, well, let's make it 10 because I think we're running behind. So let's take a quick break and we'll go on to some more cool stuff. You take a look. This is the prototype range. So please don't take the board. These are downloadable 3P. We sell them. Yeah, print your own. However, we are going to sell a kit for these.
Is this what you buy?
You buy this. You buy the board and the file. This case, we will sell separately.
You know when the case is going to be available?
A month or two. We're still working on it. I don't like this case. I don't have language here because you need to have a slide. So I'm still working on it. So.
But the files are out there now?
The files are out there now. That file is not out there. It's not the official Rogue logo. That's the Rogue logo. That's the engineering logo. The engineering department came up with this. The marketing department said no. They do. I mean, come on, guys. Look at these. Which one would you rather have? What? Oh yeah. Yeah, it's a little more stylish, but they said it looked like a video game.
And I'm sorry, it comes with these pins?
Yeah, it comes with the flywires. Yeah, so you get the board and the flywires.
I've been watching this project.
That's the yeah.
Actually, okay. And I was like looking for it.
Yeah, I can see them saying
the public. I was like,
It's a video game. Yeah, they said, we can't do that. It's a video game logo.
I have 3 fingers. I am professional. You guys have to buy our collab and see it. Because we're getting the new ones.
All I can take.
Two alternators, not a big fan. Yeah, we see them in the summer, so we can see that or you don't have to see that?
I have one.
So,
How much are the DMC vectors?
Oh, I know. $29 or something like that. $19.99. No. Yeah, I believe that. I don't know. I just go down and stop.
What are you saying the hardware difference was between what's currently in the store and what's going to be on the next product?
I put some protection diodes on the logic analyzer. I tied the FTDI chip on the MC so we can crank up the baud rate.
So you're using USB, it matches the
It matches, right. And, well, it matches yours. And then I put some more bulk capacitor on because it was browning out the processor cheap.
It has a 4th axis.
Not as fast.
And so we do crazy PCB etching. I got a lot of toys that are
Not the Jeep.
pretty crazy.
But they're very minimal. I mean, it's not,
So basically, as long as you're using a decent SD card,
you're not a problem. K-Center or SanDisk.
Well, you're not going to go Ultra HX or whatever the format is. So I bought one on Amazon to try to use it in a data logger, and it just would not accept it. I'm like, what the hell is the problem? Come to find out, it was the standard size or whatever the size.
Oh.
So if it's an UXHD SD card, I'm like,
This is a micro SD, and it's
because they're cheap now. Like it doesn't matter their capacity; it's relatively inexpensive.
sure.
And I didn't realize that like certain SD cards had certain like requirements and stuff like that. I was like, that's ridiculous.
Can I give you one suggestion? The screen on the left is just bigger and clearer.
Oh,
easier
I'll
to
sit
see
over. Okay, I'll sit over
on the
there.
back. I was wondering if you're...
Yeah, can I switch sides? I can switch sides.
Yeah. Does the
Okay.
camera need to be adjusted at all? But I just thought to help the folks.
I know, Giselle's got to do the camera.
Okay.
Can everybody hear me?
Oh, yeah. I can hear you. I'm in the back.
All right, good. I got it off.
so the current version, as long as you're not being an idiot with your digital inputs and you're not using a cheap SSD card,
You're fine.
really good.
But I'm always an idiot when I debug.
Well, that's why we put the protection resistors at Because we have one very intelligent idiot called John Day.
You hired the new guy.
Yeah. And he didn't blow it out, but he almost blew it out. I think, and I don't know this for sure, but I believe that the port key is 5.
So I was a big.
I have to check.
If you're always doing 3.3
You're fine. I have to check to make sure that.
Yeah, John and School were gracious enough to look into beta user.
So-
I had a lot of fun testing that.
The extra speed you get out of the USB, if you're just like watching waveforms on the screen, can you actually perceive any difference there? Or that's mostly
We're the Wi-Fi is almost the same.
I know, I was talking about like between F and G.
When you look at the.
We haven't, we have not implemented higher speed yet. So we're still working on it. But the hardware's clearly on the software.
Are you gonna say pick one up in the
Hardware is software.
Yeah, so I'm suspecting you're.
I know I can get 5 meg for Wi-Fi, do the same thing, but that's what it is on Wi-Fi.
I wouldn't think you'd really like a huge noticeable difference in the waveforms, but
Well, you know, the big deal is when we return the waveform, we're turning on data. So the faster we do that, the faster we get data.
Right, I'm just saying, like, because you're already looking at live view, you might be able to get a few more frames per second.
Exactly, we probably get about 2 more frames per second.
I would think the bigger difference is going to be once you have the data logged in, you want to download
Huge
200 megs. of data.
Exactly. And the other thing, yes, exactly.
But then for that aspect, you're probably like the SDs come out when you do it.
Right.
Is the resources support offline operation if you buy it, it's fine with that, if you have to download it?
Excellent. Anything on your web page?
You have to buy an SD. So we publish all the pages on our site. Yeah, you can download them on the SD.
But you were saying if you're using the iOS app or the Android app,
You don't
it's
need
built in, so you don't need the web pages.
So you can just, right. So you have to buy an SD, micro SD.
What about since it's web-based, like a Raspberry Pi or something?
It actually works on a Raspberry Pi. I'm gonna laugh at you because the web pages run so slow. It has nothing to do with the OpenScope. It has everything to do with running the web page on the Raspberry. It's like, why? Your phone does better.
Yeah, but I have a bias against the display at this size.
Okay. Yeah, well, with the Raspberry Pi, you're probably plugging in or something.
Pardon me?
You're probably plugging in the Raspberry Pi. Right? So you use a putty, you actually have a monitor tied to it.
I have a monitor on the area.
Oh, okay. I usually use a putty when I use the Raspberry Pi.
You always do it on an iPad, that would be nice.
I saw Phil's as well.
Well, Android, I have an Android pad. I bought one of the original iPads and it only lasted about a year and a half, so.
Yes.
That's yes.
Are there any plans to make like a Windows desktop app that you could use where it would be native so you could just use it directly between a computer without having to use the SD card on the side?
That's what we're doing.
No, I'm talking about like if you're out in the field and just want to look at it on your computer, so one has web pages hosted on the computer instead of having.
Actually, the Digilent agent, it's not working right now. The Digilent agent has it in there. So you can go to the Digilent agent and see all the nodes on, and it takes the pages from the Digilent agent, copies and
Okay, so once you initialize it on your computer where you have it,
right,
you
you should be able to do it. Right now, there's a bug, it's missing two wonderful pages. So I gotta tell Sam to do those pages.
But once there's enough.
Yeah, there's enough to able to do it. Right, yeah.
Yeah, that would work well.
Yeah, so
that would address your issue.
yeah, so, yeah. You go to the Digilent agent. It'll say launch waveforms live, so all the pages come from the Digilent agent.
Okay.
They don't come from the R servers.
If you're actually connected to the internet when you launch it from there, does it go pull the latest from the live version if it's
When
available?
you do that, you're saying, I want to use it, that's what it's. So,
This is the presentation on the front.
yes. Yes. It's on, yes, it's on the thumb drive. We're looking at them. It's there. I think we need to get going again.
So the part of this that's open source, that's just the MZ firmware that's open source
And the schematics.
and the schematics. Is there an option like we did an NDA where we could see the board layout? Because the thing that I'm interested in is learning more of the layout techniques you were using to get such good signal voice stuff.
I would say yes. The answer to that question is fundamentally yes.
Okay.
But we would have to be buddies. All right, I think, can we roust everybody in? Can you get everybody? We need to get going because we got a lot to cover yet.
What, really?
Yes, we're a third of the way through. Bob, good for you. I don't feel bad about giving you. All right. Yes.
Why is that MCU?
Because it's got great ADCs on it.
That's why. Because there's a lot of 32-bit.
They don't have ADCs on them. They're 3.125 megahertz.
Password.
At 12 bits.
Okay.
So I figured if I just.
Yeah, that took about what, $8 off the price of the MCU. I can't say this, but the MCU is probably cheaper than that.
Wow.
So the MCU was cheaper than the ADC we would have to put down.
Wow.
So, yeah.
Yeah, that's cool.
This whole thing was designed, this is very confidential, but I'll tell you anyway. I'll probably get fired, which I don't care, but COGS on this is under $35. So.
That's really not that uncommon when it comes to like mass consumer products.
Right. And of course, we do them in large quantities, the price goes down.
That's awesome.
So, yeah, I designed, I was pinching a penny. If I could find something that was a penny cheaper, I put it there, and it would work. I did a lot of part swapping, a lot of hand part swapping.
Is that like an American bomb or is that oversourced or overseas?
I cannot confirm or deny that. That's too much confidential.
I get asked for competitive bombs all the time. I'm like, well, I don't know what the China pricing is going to be because that can be anything from.
I can't tell you it's manufactured in Taiwan.
Oh, okay.
There you go. Let's go on. DMA usage. This is a 200 megahertz processor. It's not the fastest thing in the world. And yet I'm running multiple instruments concurrently. Only way I can do that is to push this down into the hardware and not involve the CPU. DMA is your friend. Like I said, I could have used 14 DMAs on this part. There are 8. So as I got into the data logger, I started reallocating the DMAs, which means that certain instruments couldn't be used while other instruments were being used. In this particular revision that we're talking about today, you cannot use the logic analyzer and the waveform generator at the same time because they use the same DMA. And the reason why I picked those two peripherals was because they both needed to run at the highest DMA priority to get on the I/O bus, and since they both needed highest priority, and that wouldn't work because one's going to stall the other, I decided to say if I'm running the wave gen, I'm not going to run the logic analyzer. If I'm running the logic analyzer, I'm not going to run the wave gen. And I stole that DMA. But DMA works in parallel with the CPU. It's down in the hardware. It's like having fabric. It's like having an FPGA out there, only it's hard coded. And so once you set up all the DMAs, the instruments run, no CPU in it. So the CPU can go off and run the Wi-Fi stack and link the LEDs and do other things. And the other nice thing about the microchip DMAs is any peripheral can trigger it. Timers, OCs, anything that's got an interrupt can trigger a DMA, the full suite. So the DMAs have a great architecture. That's not true of all the other peripherals. Like the ADCs can only be triggered by a handful of things, like 2 OCs and 2 timers and an external trigger. That's all will trigger the ADCs. So I had to be very careful in my resource allocation to make sure I got the triggers to the ADC, and then the DMAs I just picked up things that weren't in use because DMAs work on everything, which is very nice. When a DMA triggers, there's no ISR required. I mean, it's just an event. The event goes from one peripheral to the next, and it's edge triggered, and it just goes. So there's no ISRs involved. There's no CPU code involved when triggering a DMA from another peripheral. And of course, the DMA is going to run way faster than the CPU can transfer memory or anything like that. 50 mega transfers a second is sort of what it can do when it's running full out. So yeah, it's really quite good to use the DMAs. The problem with the DMA is it runs right into physical memory. And on the MZ, both flash and RAM have cache. So, and when you run from the CPU, by default, it's going to go to the cache. But the DMA is going to put it in physical. So what's really ugly is the DMA can transfer some memory, and then if you go from the CPU to read the memory, you might not read the right data because you're reading out of the cache, not the physical memory. So on the MZ, you have it's got virtual addressing. You can either have KSEG 0, which is the cached addressing, or you can use KSEG 1, which is non-cached addressing virtual address. So when you're done DMAing and you want to actually look in the memory, you have to make sure you use the right KSEG 1 virtual addressing mode to get to the physical memory. So there is a cache coherency problem that you have to really pay attention to. Fortunately, in coding, as we all know, when we get done with a project, it's not that we have too few memory copies, it's always we have too many memory copies, and we're trying to get rid of how many times did I copy the memory. So really, it's not a problem. All I did in the code is when first time I had to do a memory copy, which I did have to do, because remember these buffers are full of ADC values, not millivolt values, and I had to translate them. When I do that, that's when I actually transfer from KSEG 1 to KSEG 0. So by the time I'm actually doing other processing, all the caches are updated. I can just use a regular virtual addressing. So on that first copy, I get it into the cache, and then I can just, like I say, run the code normal. But you got to be careful when you do that, and you got to be careful that you actually did do that. And so you got to watch your code. Fortunately, when you don't do it, you know, it doesn't work. There's a couple ways that you can get to the KSEG 1 virtual address. You can define with the compiler an attribute called coherent. And if you have a buffer declared with the coherent attribute, it tells the compiler to use the KSEG 1 virtual addressing mode. Go directly to the physical memory. That works fine unless you put this in the structure definition and it's ignored in the structure definition. How do I know this? Because I tried it and it didn't work, and I had to call up Json, and Json said that doesn't work. So, but this will work in static variables and stuff like that. But that's one way. Another way to do it is I just made a macro that converted the cached address to the non-cached address. And you can do that. It's just one bit you got to mask off, and it changes the addressing. The trick, if you don't have some place where you're copying the memory anyway, and you want to get coherent, if you talk to MIPS, what they say is, oh, you got to go into the TLB and you got to see what's in the cache, and you got to clear out the cache line, and no, just mem copy from the non-cache to the cache memory address and be done with it. It's very quick, very easy, but right in your C code. So if you look at the source code, there's one or two places where I do this mem copy from the KSEG 0 to KSEG 1 right on top of itself. And all I'm doing is making the caches coherent in that case. And I do that in the UART. I do that in one place in the UART. A really ugly thing is MPLAB-X, no matter what addressing mode you decide to select, MPLAB-X always looks at the cache memory. And another ugly thing about MPLAB-X is if you go in and look at memory, like in the memory view, it actually will change your cache because it has a debug exec that's actually looking at the memory, which causes the hardware to do things. And so it can actually change what's in your cache. So chasing physical memory down in MPLABX is a real pain in the neck. So what did I do to get around this problem is I put my little mem copy in before I actually set the breakpoint to look at the memory. And of course I took that out on the debug, after debugging I took it out. But I just put it in the cache. I just mem copied it into the cache, and then I could look at it next and get the right number. And then when it was done, comment it out and keep going. So you might see a couple of mem copies copied out of the source code too, and that's because I was trying to see what was actually in the memory. Some other things about the DMA are, so this is all empirical data. How fast can you trigger a cell transfer in DMA? They don't tell you. How often can I say cell transfer, cell transfer? Take a timer, how fast can I run the timer? Trigger, trigger, trigger. There's nothing in the data sheet that tells you. Well, come on. I/O bus runs at 50 megahertz. The internal RAM bus runs at 100. What do you think? Oh, 50 megahertz. You would think you could trigger at 50 megahertz. So I put it at 50 megahertz. I was getting like 7. That doesn't look right. So I started slowing it down and speeding up. What I found is with one DMA, as I triggered it faster and faster and faster, when I hit 14.7 mega triggers per second, cut in half. I was missing every other trigger. So 15 mega triggers per second is as fast as I can trigger the DMA, and that's only using one. The problem is when I start turning on more, that number drops, and it's empirical. You just have to figure it out. You got to just run tests. And when you turn on all 8, we're down to about 10 mega triggers per second, and we are right on the boundary. If I start causing stalling, and I had to do a lot of tricks to make sure that I didn't trigger 2 DMAs exactly at the same time. Well, I could do 2, but I couldn't do 3. If I did that, then I caused stalling, and I couldn't even do 10. I had to drop to 5. So I had to go through and very carefully make sure that when I ran the instruments, so like for example, when I run 2 DMAs on the ADC inputs, they're staggered, so they aren't triggering on top of each other. Now, the WaveGen could be run at a totally different frequency than the ADCs, and they would occasionally, 2 triggers could occur right on top of each other. And it was okay as long as it was a 3 or under, I could still do 10. If I had 4 DMAs lined up on top of each other, I can't even do 10. And so that you just have to figure out. And how did I do this? I put it out on the oscilloscope, and I waited until my wave turned. I said, okay, it's not working right anymore. The DMA can transfer a maximum of 64K bytes. It really can't even do that. There's a thing we call freakout mode. The way you just declare 64K exactly in the DMA is to put a 0 in the size because it's a short. And when you do that, the DMA bad things happen. It doesn't stop working, but the trigger rate goes to hell in a handbasket. It starts screwing up the bus. It starts stalling and delaying other DMAs. It was just, and I'm not even pretending what's going on. I don't understand what's going on, but all I know is you don't want to transfer 64K. Back it off, just a couple of bytes. Just get a couple bytes off, and we back off 4 bytes. So, or 64K minus 4 is what the buffer size is. The other thing that I found that was a little discouraging, all the cell transfers are serialized, even if you're on different buses. And what this actually happened was we were hoping to get a 50 mega sample per second logic analyzer. And the way I was going to do that is I was going to trigger a 64K transfer right off of port E. Let the DMA run as fast as the I/O bus would run for that full 64K. But that's a single cell. The problem was once I triggered that cell, the UART would never trigger. And even though that was on totally different buses and totally different banks of memory, the other UART, so the UART stopped. It completely stopped. No DMA transfers occurred. And so it was a little discouraging, but what I learned is DMA serializes the cell transfers. And it's by priority. Whatever the highest priority is, that's the cell that's going. And it's irrespective of the buses or banks in use. So these are kind of like some of the subtleties you trip over when using the DMA. So the next topic here is ADC interleaving. I use the DMAs very heavily. I use the peripherals I use OC and the timers. Let's kind of go over what happens. Let's keep it easy. got an ADC, I'm going to trigger it at some rate. That's the sample rate. Trigger it, converts, the conversion completes. When the complete event occurs, I trigger the DMA to move the data out into the memory buffer. I just let the memory buffer tell the DMA to auto re-enable, so it just spins around and around in the buffer, transferring it on the complete. But that would give me only 3.125 megasamples per second, because that's the fastest I can run an ADC in the MZ. I want to run faster. I want it to at least be 1 megahertz stroke. So I interleave 2 of them. And the way I did that is, of course, I got the system clock running at 200 megahertz. My peripheral bus is 100 megahertz. I hit my timer. Okay, we got that. I got a timer that's going to trigger the ADC. But then I also had the same timer, so this is synchronized, fully synchronized, to run an OC. And the OC was set so it was logically halfway. This would trigger, and then, 320 nanoseconds later, this would trigger. And 320 nanoseconds later, that would trigger. And they would trigger these ADCs. So these ADCs are staggered, converting. They get completion events, the DMA then. And of course, my result buffers, I got, this is every even sample, this is every odd sample. That's what my result buffer looks like. DMA in here. And this works well because these DMA triggers are staggered, which is good. Because I don't want to line them up on top of each other. I know they're staggered. So I know I'm not going to disrupt my 10 megasamples per second with those. Now there's some tricks. This occurs at PR match plus 2 sysclocks, basically when it rolls. That's when the event occurs. This event occurs technically 1 PB plus 2 sysclocks later. Okay, so these events these peripherals don't exactly work at the same timing. I'm getting ahead of myself. So you have to play with the timing a little bit on these things, and we'll look at that a little bit later, how we play with the timing to get these things actually to be perfectly halfway out of phase as it's sampling.
So why didn't you just use a flip-flop?
Because that's an external component.
That gives you an exact 50%.
I know, but I don't want to put the pins down or buy the flip-flop. I'm going to do this all inside the
There's
MZ.
nothing on the top part that will work that way?
No, this is
So these 16F parts have that built in.
No, this is an MZ. Yeah, this actually, yeah, what?
So you're interleaving 2 DMAs to get your frequency up on each of the channels.
No, I'm actually, the DMAs are so far down chain, I'm interleaving here.
Yeah, sorry. But I mean, so you're using 2 ADCs for this one, 2 ADCs for that one.
Yeah.
Is there anything that would stop you from doing in the software where you use all 4 for one channel?
Nope, I've done that. Okay, side note. I first got the MZ, I didn't read the data sheet. I ran the oscillators out of range. The MXs can go down to 4 megahertz on the input of the oscillator. The MZs can only go down to 5. I ran it at 4, thinking it was like an MX. Turned out the PLL captured not at 200 megahertz, but at 400 megahertz. And it seemed to run. So then I interleaved all 4 ADCs together, and I actually got a sample rate of almost 25 megasamples per second. Now Larry over here said, "What are you doing, burning up the chip?" It did get warm, believe me. But yes, you can.
The ADCs have sample and holds in the front?
Yeah. The dedicated ones are 6 of them, so there's 6 sample holes.
What's the window on the sample?
It's programmable. So, some things I learned about the ADC, and Ajay finally figured it out. But he figured it out after I made the slides. So it starts out for some unknown reason, except Ajay knows the reason. Even though the ADCs are on and warmed up, these are very complicated ADCs. The initialization routine, you turn them on, you gotta warm them up. There's a warm-up time period you have to run them for, and then you keep them on. Okay? But the problem that I was finding is if I wasn't converting, even though they were on, if I wasn't converting the first conversion, it gave me a slightly off value, several millivolts, but slightly off. So I learned I gotta just throw out the first or second sample. I just gotta get it going and just throw them out. then I got good conversions. Well, Ajay found out that they cooled off. The converter wasn't running, they're cooling off, and they shipped it. And if I did this all over again, what I would do is I'd just turn on the ADCs and run them full speed all the time. But I didn't know that when we started the firmware, and this is how I did it. So then I had, well, what do I do now? Okay, I'll just run it for samples, and gets it running. Know it, if you use these ADCs, throw out the first few samples. Get them running, throw them out. And you'd be a lot happier. The other problem I had was, if you read the OC documentation, it says the event occurs on the falling edge of the OC. Except they hardwired the ADCs to the OC, and the ADCs actually trigger on the rising edge of OC. It took me a long time to figure out what was going on with that. So the documentation is wrong. It actually triggers on the rising edge of OC. And by the way, the timing that they give you in the OC documentation has nothing to do with the timing between the OC and the ADC here. So everything is empirically determined. So here is what points look like on a properly interleaved ADC. You can see that nice correlation. Looks like it's all coming off in one ADC. It's really two. Every other point is a different ADC.
So if you've got problems with that, that'll show up in your Fourier transform.
There you well, it'll show up here.
Well, I mean,
Oh.
you can have stuff that's subtle. You can't see there, but you'll see it in your transform.
You know, at these time frequencies, it was actually pretty easy to see here. This is what it looks like when you don't have it right. It's obvious. And it is obvious. It was just totally obvious when it wasn't right. And there's another thing can happen. You can be triggering backwards, and you get that. All of the above has been done. And it took me quite a while to ensure that the right ADC fired first, and to get the timing right, and it was all done empirically.
Tried at 500 megahertz someday.
Yeah. So that's interleaving of the ADCs. Let's go in. Yes, Brian.
For the ADC capture, do you always capture the exact amount of data that's going to be displayed on the screen, or do you oversample and then decimate so that you get more data to show? You know what I mean?
I know exactly what you're talking about. So the question is capturing done at the same sample rate as the display, and is the amount, the buffer size, the same as the buffers used in capture? The answer is sort of. The buffer size is always, and we'll see later, 32K plus samples. Always. That's my DMA target buffer. And I will we'll go over this, and I will overlay the requested buffer size on top. The sample rate comes directly from what is asked of me as a sample rate. So I will change the timer in the OC. And in fact, if the sample rate goes low enough, I will drop off interleaving, and I'll just go down to the OC. I would do that differently had I known how these ADCs work. I would have run the ADCs at full speed all the time. And this is exactly how I do the the data log, because I use the averaging on the data logger. What I do in the data logger is I run the ADC full speed, I run it through the averaging hardware, and I transfer that into a single memory location, and then I run a second timer on the DMA to transfer it out of that location at the sample rate. And that's how I would actually do this if I was to do it. The problem is that it uses more DMAs and more timers. I'm already out of DMAs and I'm out of timers, so it's a resource problem. Any other questions? Let's go into the logic analyzer. Logic analyzer is simple. There's no analog circuits, it's all digital. Thanks, I've been back in my home territory. It's a simple thing. So I got port E. John here?
Yeah.
Is port E 5-volt tolerant? Is Larry here?
I haven't gotten another data yet.
Right.
I can answer for you in a second. So.
Okay. Someone asked me if the logic analyzer is 5-volt
I'll look it
tolerant.
up and I'll answer in just a second.
Yeah, I'll let you look and I'll keep going.
Keep going. Yeah.
All right. So we take port E, which has got 10 bits on it, and all we do is we take a clock at our sample rate, and we DMA port E into our result buffer. Oh, isn't that so simple and easy? Finally. that's really, you know, and because the DMA has this sampling rate problem, I can only run it in 10 megasamples per second. I really, really, really wanted to do a 50 megasample per one. We actually average, if you look on the box, turn your box over, it says 50 megahertz sample rate. That's because the box was made before I wrote the code.
Yeah, refund?
No. So, and I actually have software that'll actually run it at 50, but I can't run anything else. That's all I can run. And so I couldn't run the UART, so I had to give up on that. The other thing is because with the same with the function generator, the logic analyzer, I got to bring those points in at a very regular rate, obviously because you want the sample rate. I must run the DMA at the highest priority because I cannot have any other DMA in the system stalled. So it's got to run at the highest priority. Right.
Keith, what's the fastest sample rate that you can run the logic analyzer so that you can guarantee you never skip samples if you're just like streaming to PC? And if I wanted to store a day's worth of samples, how slow do you have to go so that you can guarantee you never miss one?
Is that the only thing you're running? Only DMA?
Well, no, all I'm running is the logic analyzer, part of the OpenScope. Right, so I write a client that's just constantly
10 megasamples is as fast as we'll let you run.
I understand that's the fastest one. That won't guarantee me non-missed samples between captures, right? So if I want to stream, I just keep asking, you know, give me this sample, give me the next one, give me the next one over a day, right?
Mm-hmm.
If you run it slow enough, you're going to be able to get all the data without any
32,000 points is what the DMA, what the target buffer will be, is 32,000. Otherwise, the target buffer will roll. And we don't, on the logic analyzer, we don't store it to the SD card, we don't do the caching. So our buffer window is 32,000 points.
Okay.
So when it's full, it's got to be processed,
It's
right?
not double buffered to do continuous capture.
No, but the data logger will.
Right.
And the fastest we'll run the data logger is 50 millisamples per second. Because I got to write to the SD card, and that's slow, right? So that's what's limiting me there. But because I had to slow it down for that, I also did averaging. So your point is much more stable. I do 16 over averaging on that. So your point is, and I do that hardware. It's much more stable than you know, just one sample, one SAR conversion. So now we're going to get in
D or E?
E.
Oh, D is definitely 5-volt tolerant so far, and it looks like E, much of E is as well.
Much of E, not all of E.
So, so I got to know exactly which E's we're on, but so far E0 through 3 are definitely there.
E0 through what?
0 through 3 so far. I'm just going through the pinout
Okay.
right now. I'm not saying the rest aren't. I'm just going through the pinout.
Okay.
I'm just going to go page
I'll let
by
you
page.
continue to look. So this, by the way, is a very hard section. Triggering is conceptually, you got to think of everything. There's lots of little corner cases. Now, I mean, we're going to start out with easy triggering. What is it? I have some event, and you know, okay, I'm done collecting data. No, wrong. Not even close. We have to think about all of the components of what we expect to see on the scope. We had to invent some terms because some of them are just intuitive in your mind. You don't even think about it. You're looking at the center of the scope. And your trigger usually is at the center of the scope, but maybe like you've got a chip select, you're going to push that trigger back there and you're going to look here. You're looking somewhere deeper into the signal. So where you're looking, we refer to that as a point of interest. We had to define that term because, and the point of interest is sort of like the center of the data you want. You want to see something after, you want to see something before it. And that is not necessarily the trigger. By default it is the trigger, but it's not necessarily the trigger. But all time referencing has to occur off the trigger. So here's a sort of an example.
So is this the 144 pin, pick 32?
124. So what happens is you start acquiring data, and you have pre-trigger data. You hit the trigger. This delay can be positive or negative. This is where you really want to focus on the signal, and then you need to collect data after that point too. So it isn't like I hit the trigger and I stop collecting data. No, you got to collect data after. And the problem is, where is this trigger? Where's your point of interest? And that kind of defines how much data you want to collect before and after. It isn't just a simple I hit the trigger and stop. It's not even a simple I want to collect this in the buffer and then collect half a buffer later. It's not that simple because you got this trigger delay in there, and this trigger delay can be positive or negative. So we had to define some terms. Start of acquisition, where we turn on the thing. Actually, there's another point we didn't talk about when we enable the trigger. When the trigger occurs, where our user's focus is, then how much data we have to collect after the user's focus. And then, on top of that, we have a buffer, which is a variable size of what the Waveforms Lab has actually asked us, because we're collecting the full 32K, but he may only ask for 3K samples. So we have to superimpose that buffer on where the data is. Now there's also a lot of other things that are going to happen. This trigger, of course, is going to occur somewhere in the DMA when the DMA is running. And it's not always going to be at the beginning or at the middle or at some point. We're going to have to rotate that buffer around to where we can say, here's where the trigger is, here's the point of interest, this is the data buffer we want to get. So we have to scroll it around. And with the interleaving, we got to uninterleave it as well. We got to re-stitch together the data in 0.0, 1, 2, 3, 4. So there's a lot of things going on. So here's my 64K buffer that I've declared in memory. And that's always there. You can look at the code, 64K defined for oscilloscope 1. Now we got to back off a little bit because we'll go in freakout mode if we do a full 64 DMA trigger. So we back off 2 samples, that's 4 bytes. We back it off. So the DMA size is actually 4 bytes less. So the DMA is going to be this size. Now, I gotta, minimally, when I start data collection, I gotta throw out a bunch of points because the ADC's first few points are crappy. And so I just run 64 samples before I even enable anything. I just get it going, and this is just slop. I just let it run, I will never use those points. Then I start acquisition, and there will be a valid 32,638 number of samples of acquisition that will occur. And this is slop for when I want to stop. Because the problem is when I stop, I have a timer trigger an ISR, and the ISR then turns off the timer that runs all of the ADCs. That takes time. And I can be taking a few samples can occur, and I need room. I don't know how many samples it's going to be, and I don't care because it's after the stop, but I don't want it to wrap around and destroy the data at the beginning of the buffer, so I need some slop at the end of the buffer. So this is slop at the beginning to let the ADCs warm up. This is slop at the end before I turn off the DMAs. This is slop because I can't run the DMAs at a full 64K. So therefore, this is the actual acquisition buffer of valid data. And then depending on where the trigger is, I gotta scroll this all around to get the trigger lined up, and then I superimpose the buffer that is requested from me from Waveform Live on top of that. That's what I actually hand back to the browser. That can be, well, that was some interesting code, right? But it gets even more complicated because of this delay. The point of interest in the trigger can be positive or negative. Well, let's talk about some more stuff. So I start acquisition. I get some pre-triggered data. The problem is, wherever that point of interest is, wherever that trigger is, I can't turn on the trigger until I have acquired enough data, at least up to the trigger in the buffer. So I turn on acquisition, run those 64 samples of slop to get the ADCs warm, and then I run and collect enough data to get at least because the trigger could occur right away, enough to get the pre-trigger data. Yes.
Your requested buffer is the point of interest always centered in your
We try to. We're going to talk to it. We try to always center the point, but we always can't.
If your trigger delay was negative, your requested buffer would be the other.
Right. but that only works to a point. We'll go over it. The answer is point of interest always in the center of the requested buffer, and the answer is we try, but we can't always do it. So we have to let it run at least that long up to whatever the pre-trigger date is, so that we have that in our buffer, so if the trigger happens, we know we have that in the buffer. Then we enable the trigger. Trigger could occur right away, or it might not. We wait for the trigger. Once the trigger occurs, we have to know how far it is from here to here, and we set a timer for that amount of time, and when the timer expires, it calls an ISR, and then I turn everything off. The point of interest really isn't part of that. What's really part of that is the delta between the trigger and the end of the buffer, because my time sync comes when the trigger comes. That's the only place I know where I know I'm at. So the point of interest is interesting to the user, but not so much interesting to me. Yes?
Is that minimum trigger data like dynamic? Because you don't know
Yes.
okay, so it's like a running circular buffer of a max size, and then when it triggers, it stores it and then acquires more from it.
Right.
Okay.
And so I acquire so much data before I enable the trigger that I need to have, I know I must have, if it's an instantaneous trigger. And then it just runs. It might be an instantaneous, it might not. But if it's not, then I know I still got the pre-trigger data.
Right.
And then once the trigger occurs, it's always circular. And when the trigger occurs, I run for the rest of the time, and I get it. Let's see here. So now we get into the corner cases. Let's talk about a negative delay. Negative delay is the point of interest is actually before the trigger. Now, if it's right before the trigger, that's no big deal. It's in our buffer. We've obviously been collecting data, and the trigger occurs, and we got stuff before the trigger. But we only got stuff at a maximum of one buffer. Obviously, we can't collect any more than what's in our buffer, and if this delay is greater than a buffer, when the trigger occurs, we're not going to have the point of interest in the buffer. We're just not. It's too early. So you can only look back before the trigger one buffer for every 2K samples. Now that doesn't mean you can't specify it longer. You can. It's just you're not going to get the point of interest. What we will display back to you is the trigger on the far rightmost side of the screen, and as far as we can with the buffer. And that's what we're doing. Best we can do, because we don't have any data. Now let's talk about positive delays. That's a little different story. Positive delay, trigger occurs, we're not going to have the trigger in our buffer, but we are going to have a point of interest. And this is a very complex heuristic. Let's see if I have it here. Let's go back. This is a very complex heuristic. What we will do is we'll try to still center that point of interest because we can. Okay, we won't have a trigger, but we'll have a point of interest. And we'll try to center it. But if the trigger and the point of interest can both fit in the buffer, we'll scroll things over in the buffer. So this point of interest will start, as your delay goes up, it'll start moving over, and then boom, it'll come back because we lost the trigger, so we might as well give you what you're looking for. And we just assume that having the trigger and point of interest that will be displayed is more important than centering the point of interest.
So how do you define the point of interest? What is that?
The center of the display when you scroll on Waveforms Live. You go in Waveforms Live and you scroll that thing back and forth, and it's implicitly taking the center of the display as your point of interest. You don't realize you're doing it, but it's there.
So that would be like if you're looking at a single digital transition, so that's your trigger point.
And then you move the trigger back.
So you're moving it.
Yeah, that's your chip select or whatever. You move it back here, and you're now centering the display here.
So you can actually move your trigger off the buffer screen.
Sure. And you can see that. You can see that. You can just completely. So, one of the things that's difficult, all of these pointers are all calculated up front. They're not calculated after I capture. They're all calculated. And they're all referenced around the trigger. You say, wait a second, what if the trigger is not in the buffer? How can I reference the time reference against the trigger? It's modulo math. I just modulo the buffer size of the trigger until it gets gets up there, because all I really care about is how long until I turn it off, right? So trigger occurs, I know this time to turn it off, I gotta find the point of interest. If I modulo this up, I can calculate that now, because it's just modular math to get whatever this distance is, I can do it from here. And the reason why I do this is I gotta scroll this buffer so this all lines up right, and I need to know where to scroll it to. And that's how I know the index to scroll it to, because everything is referenced timer based off the trigger, because that's the only anchor point we have that actually occurs in the acquisition. So this index is calculated up front. This index is calculated up front. This time interval is calculated up front. I start the instrument, I know how much to acquire, and when I get done, I scroll the buffer to the trigger location. I now know where the point of interest location is, it's this distance. I know where the end of the buffer is, and then superimpose the requested buffer on top of that, and send that back to the waveform slot. Questions? Gotta have questions. Okay. What triggers do we support? We support rising and falling edge. The way we do that is when you enable the trigger, the first ISR I set is against the digital compare filters, is when the signal is below your trigger point. This ensures that I am below for a rising edge signal. And when I get that ISR, I turn on the above trigger point. And when I hit that ISR, I turn on the delay timer to tell me when to stop. These are very quick interrupt routines. This just turns on this just turns on that. This stops data collection. And then of course falling edge is just the opposite. I wait until I'm above the trigger point, and then when I get there, I turn on the one below the trigger point. This is the actual trigger, is the second interrupt. In that interrupt routine, I save the DMA pointers of all the instruments. And I start the delay timer. I will also, because the trigger may disappear in the ISR, I have to search back in the buffer for, because the ISR is going to take some time to get in there. So the DMA pointer is not going to be on the trigger point, it's going to be a couple samples late. I actually have to search back to where the trigger, and I have to remember where that is. That gets very complicated, especially when you're running different instruments at different sample rates. I actually remember the time between when I took the DMA pointers and all of the buffers to where the trigger is, and I remember that in picoseconds. I don't remember it in samples. So that when I adjust later, when I adjust all the buffers, if they're a different sample rate, I know how many samples to move back to see this is what, and that's how I line up the different scope traces, because I calculate those. This, by the way, gets way more complicated here in a minute with the logic and stuff. Okay.
The scope, what trigger modes do you support?
Rising and falling edge, and you can have a gap. So you can say, by default, the gap is
more towards the auto versus normal mode.
It's all the normal.
So if you don't get a trigger, the display freezes. So there is no like oscillate.
It's all normal. And the way it works is there's always a gap between, when you set a trigger, say 1 volt, by default there's a 30 millivolt gap. We'll say we're below at 1 volt minus 30 millivolts, that's when we're below, and then we'll say we hit the trigger when we pass 1 volt. You can adjust that gap anything you want, like by default it's 30 millivolts. Why is it 30 millivolts? I have a noise floor of about 10 millivolts when the ADCs are running, and I don't want to get false triggers. So I set it a little bit higher than the noise floor, so that it won't trigger falsely. So it's a 30 millivolt gap. So now let's talk about the logic analyze. Use change notice on logic analyze. This is why the only thing I can do is trigger on rising or falling edge. I can't do pattern match. And it could be any of the pins. It's an ORing function. You can set it on any of the pins or all of the pins. It'll just trigger on the rising falling edge, or either. Change notice allows either. And it's, since there is no below threshold, above threshold in digital, it's just whenever the change notice fires, that's the trigger. And I set my timeout timer and wait for it to quit. So this first interrupt does not exist in the logic analyzer. So the triggers we support is rising edge, falling edge on the oscilloscope, rising edge, falling edge, or either edge on the logic analyzer. This actually can have a gap in it, obviously. This cannot. This is just whatever the change notice gives me, that's what it gives me. We do not support pattern. We have a mechanism where we can support pattern matching. The problem is, you know, if you turn on pattern matching in the DMA, which it has, it aborts the DMA, and I lose all my DMA pointers because it aborted it. And I can't continue to sample. So that's a wrong thing for me to do. It would be great if the DMA had just raise an interrupt when a pattern match and kept running. That would be nice. The DMA doesn't have that feature. And what I could do is I do like I do in the data logger, is I could actually run two DMAs, one running, and the second one run pattern match. And when it matches, raises the ISR and let that DMA just die, because I don't care, but the first one's still running. And I could do that on top of it. That consumes another DMA. I'm already using 8 or 9 DMAs. I don't have any more DMAs, so I can't.
So potentially you can add a software feature in the future that if you give up an instrument, you can turn on pattern match.
Yes, I could turn on pattern match.
Is that any plans?
It's not planned at this time. We're going to see how the logic analyzer goes and what kind of feedback we get. But the hardware, yeah, we could do that. We absolutely could do that. All right, now timing, multi-instrument timing. Remember, these all could be running at different sample rates. And actually where the interrupts occur for triggers are different for logic analyzer than they are for the oscilloscope, by quite a bit. So if I took a timeline for the oscilloscope, I got some data coming in on the oscilloscope, there's some sample rate occurring, whatever my sample frequency is. Then there's a conversion. You know, my starter conversion interrupt event occurs, 320 nanoseconds for conversion. If I get a trigger match, my interrupt goes into my ISR, and then there is a delay from when the DMA takes the event from the completion and actually sticks it in memory, and this is when it actually gets put in memory. And of course, the trigger event, there's a delay, the prologue code, which is about 640 nanoseconds, if nothing else is preempting it. And then that's where my ISR actually starts. But if we look at the logic analyzer, the logic analyzer uses change notice, which is right on the pin. It's before the DMA, and there's no ADC conversion. So logic analyzer comes in, if the pin gets a change notice, I get my interrupt, I'm going into my ISR, and while there is a sample rate for what the DMA is going to transfer, there's no conversion time in the ADC. So the sample, boom, it's right into the memory. The difference, assuming that this was the same sample rate, the difference is 320 nanoseconds, the conversion time. The oscilloscope is 330 nanoseconds later than the logic analyzer by the time it gets into the memory. So even though I get into these ISR routines and I look back to find the trigger, I have to realize that the oscilloscope, the DMA pointer's later for the oscilloscope than it is for the logic analyzer. And I have to adjust that 320 nanoseconds. So when I go back and I find out what this ISR to trigger time is, when I actually undo the buffers and align them up, I also add in that 320 nanoseconds difference for the oscilloscope to get them to line up with the logic analyzer. And yeah, kind of a pain in the neck, but it's there. The other problem, saying the same thing, it's going to be 320 nanoseconds later. And that comes from the conversion time of I'm running the ADCs always at 3.125 millisamples per second. And that's where 320 nanoseconds comes. So whenever I get into my trigger ISR, I just snapshot all the DMAs the trigger is, and then I adjust to align all of the different instruments together. That's always the same. We'll talk a little bit later about, I think, some of the other timing issues with that. But let's move on to an easier, well, easier but harder, the WaveGen. Are you guys getting tired?
No.
WaveGen. This is a WaveGen circuit. This is an R2R ladder. If you look closely, it's not quite an R2R ladder, but it's close. And then this is our filters, reconstruction filters, and then the output. It's going to have that same op-amp thing, you know. This is the AC signal. This is the PWM. This is the bias. There they are. They're all there. That's the output of the PIC. The PIC output pins are going to run 0 to 3.3. That's, you know, it's a digital output, so that's what you get. This is the R2R ladder. It's going to swing a full range of 3.3 volts. The R2R ladder has effective impedance of 750 ohms. I will tell you this right now, you need to look at this R2R ladder as a transmission line. It's evenly impedance, as you go through the ladder, it's evenly impedance at 750 ohms. There's a very important fact in knowing that, and we'll look at that. This is the first reconstruction filter. This is a noise filter going into the op-amp. This increases my input impedance so my feedback resistor doesn't have to be so small and I don't burn so much power. Remember, I got a 500 milliamp budget. This is coming off of the USB port. And right now, if I turn everything on, worst case, I'm burning 480 milliamps. Normal case, I'm burning 350 milliamps. So I had to increase that input impedance so my feedback resistor didn't get so low that I'm just burning too much current. That's the summing node for PWM, analog input, and DC offset. There's my bias control because, you know, this is going to run 0 to 3.3. I want this to run -3 to +3. So that's bias control to center that. Feedback, my gains. One of the things we're going to look at is that my gain is a little bigger than it should be, and we're going to look at why that is. Another reconstruction filter. This is the most aggressive one that actually smooth. I put this one in so I could produce a smooth 1 megahertz signal, even though it's down 2 dB. I could actually make a 1 megahertz signal that's pretty close to flat. The problem is it looks pretty funky at 10 megasamples per second. So I put a little more aggressive reconstruction filter in there, so at least it looks smooth, but I lost the amplitude of 1 megahertz. And then, of course, that's the PWM offset control, which we said I always run that at 2.5 maximum swing. And that offset control is going to will run this plus or minus 1.5. And the R2R ladder will give me a peak-to-peak of 3. So I can take a 3-volt signal and I can raise it up 1.5 volts, so it goes 0 to 3, or I can raise it lower down 1.5 volts, so it goes from 0 to -3. But the peak-to-peak signal that I can generate is only 3 volts. And that's the output of the R2R DAC. Okay, lots of equations here, blah, 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 blah. We're not going to use the DAC as an analog input. We're going to do a lookup kind of feature. So the only thing that we really are interested in is what is the equation for the offset. We do calibrate for that. So we figure out what those coefficients are. We're only doing it for the offset. The coefficients for the R2R ladder is not calibrated. It's actually empirically, it's best fit. It's a best fit algorithm. The way I do this is I apply each code out on port H, and I read it back, and I make a table. We're going to see that very quickly here, and it's the best sort of lookup. So the way calibration works is I put the codes out. I put this in sorted order. This table is sorted order of codes, from 0 to 4096. Sorry. 0 to 1023. And I drive the port H with those values. I drive them out. And I read them back and I make a table of what code 0, what is the voltage I get back, code 1, what is the voltage I get back. And I do this with a 0 offset, or close to 0 offset. And then I sort this table, highest voltage to lowest voltage. And I sort this in the same way. Now, when I actually run the code, I have some pattern that you have, you know, the sine wave, the triangle wave, whatever. I go in here and I find the closest voltage that matches what I want to do. And I pick that code and I put it in memory and I say, that's the code that's going to generate the closest voltage of what you want here. And I build this in memory. And then I just turn on the DMA, let this circle, turn on the DMA, pumps out port H, which then goes over to our ladder and makes your thing. So this is a best match fit. And we're going to see why I did that and just didn't do math like I did everywhere else. One of the things is R2R ladders are historically hard to make manually. The resistors vary, so there's various, the step sizes can vary a little bit. It's very hard to match, especially when you do it yourself. If you get a laser trimmed one, maybe it'll be better, but you have to buy that part. And if you think about it, the worst case is when you go from like all the least significant bits being on, most significant bits being off, and you need to go one step, turn all the least significant bits off, turn the most significant bit on. If that resistor thing is bad, that step could be more than an LSB. It could be more than several LSBs, and you're going to have missing codes. And that's ugly, especially if you're handling down an R2R ladder. You can't do, there's nothing you can do to correct that. That's just a step that's too high. You can't add anything to bring it down, and you can't subtract anything because it's going to go back to the previous code. There's also a propagation delay through that R2R ladder, as we'll see. It's actually a transmission line. And when the least significant bit switches, it takes time for that to ripple through the R2R ladder. And if the top bit changes first and the least significant bit, there's a difference in timing. And again, if it's this thing where you're turning all the lower ones off and the top one on, what happens is for a very short period of time, it looks like the whole ladder is on and you get this spike. So we're going to talk about the missing code problem first. What I did is I didn't make an R2R ladder. I reduced the resistors, and you notice that this is in the higher bits. There's a resistor. And what it did is when I switched, I guaranteed I was going down. This guaranteed I swung the error in my favor. I knew I was going to go down, not up. I can add a couple of extra LSBs to get this up where it belongs. So I can fix that in software with the lookup table. The downside of this is I'm going to lose, it's not going to be 1024, it's going to be some number of codes less. Works out the way I did it, it's right around 1,000. I got about 1,000 codes. I wasted with overlap about 24 codes. But because I did that, my dynamic range came down. I don't have 1024, I only got 1,000. So in the op amp, I just boosted the op amp an extra 2% on the gain to get that back up. And instead of being 3 millivolts per code, it's like 3.01 millivolts or something like that. But I get that dynamic range back. So now, because I forced this to go down, when I do that sort, I'm going to have a lot of codes, especially in here, and have a lot of codes that are kind of the same. So when I do that sort, I'll get them in the right order, and I'll just pick the closest one. So actually, going through the 0 point, I got a lot of codes, a lot of precision, because I got a lot of choices. So 0 is really pretty good. And then, turns out, because I got several of these, this discontinuity occurs here, it occurs here, it occurs here, it occurs here, it occurs there. But it doesn't matter, I'm sorting. So I get it. Now these are much smaller. I mean, this is a pretty big jump. The other ones get smaller and smaller. Yes?
Is there an issue where from unit to unit to unit you can have a bunch of codes that all are almost the same value, but around them you've got gaps? And
No
so
gaps. No gaps.
I mean, but like, if there's a bunch of codes that are all kind of on top of each other, doesn't that mean that then you can't produce the value just slightly more than those because they're all grouped together, or?
No, because you notice, look at this, it's still going green.
Yeah.
So the codes that are all close together, they might be closer than the average codes, but I will still have, because the least significant bit drives what my actual step is going to be, that least significant bit, of course, that's going to always be pretty close to what I want, because it is the least significant bit. That gives you that 3 millivolt step, okay? And the second most least significant bit, is 6 millivolts. Oh yeah, it might be a little bit off, but it's close, right? And that's why I didn't fiddle with the lower ones. Okay, and how did I discover where to do this, where to fiddle this? Oh, I was in the rework lab a lot, putting different resistors down. Doing this. This was, I simulated it, and I also did real research, yes.
So if you propagated those 732s down further in your
I would get
ladder,
more bumps,
you
but
get
they would
more
be
bumps,
tinier and
but they do.
tinier because
Yeah.
these are least significant bits, so they're kind of less
Yeah,
significant.
so the farther on your extremes, they just get smaller.
Right. But my biggest problem is this most significant bit, because when it flips on, it could be many LSPs wrong, and I had to get rid of that.
That's really hard to learn.
So let's talk about propagation delay. So when I first did this, I got this huge spike and I was annoyed. And I actually didn't even know what was going on. So I was sitting in Clint's office and we were like beating right against the wall, and Gene was in there saying, "This is why you can't make a DAC with an R2R ladder." So I started simulating, and I realized, I said, hey, you know, this is a transmission line. This is a equal impedance ladder that I'm doing. Transmission line and transmission delay that are significant. And I simulated this. Put these little capacitors in there. This is the, resistor to the ground plane capacitance. And I'm putting it in there. And I was tweaking. I know it's around 0.1 to 0.3 picofarads is typically what it is. I know that because I've done enough boards to know that. And I put those in, and lo and behold, I was able to simulate that spike. And it matched exactly in the same kind of direction that I was seeing on the scope. And so now I had an idea what was going on. And of course, notice I got my step down here. That's because I got that non-linearity in there. But this is where the codes go from 0 FFFF to 1 0 0 0. This is that transition in the simulation. And this is what it looks like on the scope. Now, this is after I fixed everything that I could. This is what the product looks like today. When I go through that transition, it's about 200 nanoseconds long and it's about 4 millivolts high, is what that looks like. Now, originally it was about 20 millivolts high and about 600 nanoseconds long. How did I fix that? Notice that these are really small resistors. I traded power for time. I said, well, this capacitance is quasi, I can't change it, this is what's the PCB, but I can change the ratio of the resistor to the capacitor. So I lowered those. These were originally 10Ks, 20Ks. I lowered that. And I lowered it as far as I could until I couldn't take the power hit anymore. Because by doing that, I'm consuming power, but I'm getting speed. The other thing I did, if you look at the R2R ladder, they're made with 201s. I don't know if you know what package types are, but 402s are standard size resistors. We cut that resistor size in half, and put 201s down, and then we packed them in as close as we could pack them. We were reducing capacitance in the layout. This is what we got, was that. Which Glenn said, good enough. And it's nice to see. You can actually see the steps going. Now, this is a contrived, this was a test case. This is, I didn't have my sorted DAC or anything. I was just running the codes. So that's why you get some weird stuff going on. But that's okay. I was just looking for that look when I was doing this. So now I have on our next product. Yes? Your question? Okay. On our next product, I convinced my layout guy that we were putting down 2 of these stacks. The next product, I told my layout guy, remove all the metal out from underneath the R2R ladder. And he says, no, your ductance is going to go off if you're going to have problems with the ductance. So we got a bottle of whiskey on this one. If I win, he buys me whiskey, we both drink it. If he wins, he buys a bottle of whiskey, we both drink it. And if there's no difference, we just don't drink whiskey. So we'll see on the next product if we can improve that or not. So we compared it to some off-the-shelf DACs. This is our OpenScope one. This is unfiltered, just raw data. This is 200 millivolts scale. A sine wave, obviously. This is a TI part, cheap, $4 part. That looks pretty ugly. It kind of looks like a triangle wave. It's got all kinds of crap in it. By the way, these are side-by-side comparisons. These are laid out very close, the best we could do to make it as equal as possible. This is an ADI part, $6 part. Still doesn't look great. And this is the OpenScope at $1. So I think we did pretty good on that. Break time. What time is it?
10:45.
Sweet.
So you're right on time there.
I'm right on time. Well, then we can take our full 15-minute break. Come back.
We start at 11 o'clock.
11 o'clock. Yes, sir.
On your waveform, can you upload your own patterns and generators?
The firmware will support it. Waveform lines.
And we're rolling. We're rolling. Do you guys need anything before I do anything else?
No, we're good. We're good. So let's talk about, now these are high-level concepts which make them a little easier. Let's talk about DMA stalling. When you run the DMAs, of course, they got to share resources like the bus. And they actually got to share resources among themselves, like there's arbitration logic and whatnot. So we have to be careful about how we use the DMAs. You just can't just assume they work ideally. I mean, they interact with each other, and you got to know what they're doing. Like I said, experimentally, if I just run one DMA, I can go 15 megatriggers per second. As I turn on more and more DMAs, as you can imagine, the arbitration logic starts kicking in, the triggering logic, and that starts to drop as you turn on more DMAs. And all experimentally found, I'm finding that the way I use the OpenScope, I got 10 megatriggers per second. However, if I was sloppy in using the DMAs, I would have to drop that down to 5 megatriggers per second. But I was careful and I qualified it and I tested it. Again, the way the OpenScope is defined today, you can get 10 megatriggers per second. Only the highest priority DML cell transfer will run. So once the DMA triggers a cell, the highest cell will run. Now, I'm not sure about some details of this. It didn't matter to me, so I didn't go track it out. But a DMA transfer can be up to 32 bits. If it's more than 32 bits, there's actually 2 transfers. So 8 bits, 16 bits, 24 bits, 32-bit transfer occurs in one transfer. And I'm not sure if a higher priority DMA gets fired, if it will interrupt the cell transfer and start on the next 32-bit value of the transfer. It might. But in general, in my mind, and the way I was doing it, what I observed was the highest cell transfer runs, and since I'm only transferring 16 bits, it doesn't really matter. The only time I'll get interrupted with a higher DMA is if at the end of the transfer, the cell transfer. But during the cell transfer, nothing will interrupt it. It will complete the cell transfer. So what will happen there is you've got a transfer. If you get 2 transfers right on top of each other, the higher one will take the cell transfer, and the lower one stall until the transfer is complete. In my case, since it's only 16 bits, it's stalled until after the 16 bits is done, and you'll get a delay. So you really don't want to line up the triggers on top of each other. But unfortunately, when you have different sample rates and stuff like that, you can't control it. There's some of them I can control at the interleave, but some of them, wave gen versus the oscilloscope, I couldn't control. So I had to say, what is the maximum number of things that could happen at one time? And I had to test it to see if I could still do 10 megatriggers per second, and I can't. Again, all experimentally carried out. Various system buses have different speeds. I think I was corrected on my RAM to RAM as being 50 and not 100, but I actually believe I measured 100. So this number may be wrong, maybe 50. I know that the I/O bus can only run with a transfer rate of 50 megatransfers a second. And that's after the cell is triggered, that's transferring the cell. But different buses do have different speeds, so and what can be kind of annoying here is if you got a high priority DMA cell transfer on a very slow bus, the other ones are going to wait, even if they have faster buses, they're going to wait until the cell transfer is complete. And so you can slow down somebody else. Like I say, a cell transfer, it transfers maximum 32 bits at the highest in one transfer. If your cell size is greater than that, it'll do multiple transfers at the bus level, but it'll run at the bus speed, so at 50 megatransfers a second. And like I say, a transfer will complete before before a higher DMA will start. I don't know if that's on a 32-bit boundary, if that's a whole cell, but what it's currently doing, at least at 32 bits, will complete before a higher DMA will inject and take it over. Function generator and logic analyzer, they have to occur at regular intervals, otherwise you get quantization error in the signal. So I put these at the top priority. And I don't put the ADCs. You go, well, wait a minute, you want to put the ADCs at the top priority? But I don't have to, because the ADCs are putting the result in the result buffer, and that result buffer is stable for 320 nanoseconds. I got time to get it out of there. I can be stalled. The ADC, the DMA that's reading out the result buffer, the ADCs can be stalled, and I still won't lose anything because it's in the result buffer. But going to the ports, I have to keep regular timing. So that's why the logic analyzer and the AWG have to be the highest priority. And since I needed an extra DMA, I shared the DMA between those two things, and I don't allow you to run both at the same time. Because if I did, let's say I did have another DMA, they'd both be running at the top priority, and they would occasionally, one would stall the other because of the same priority, once they stall the other, they hit. And that would give me quantization error. So I said, if I'm going to steal a DMA, I'm going to steal it from this time. I'm going to prevent you from using the other instrument while you're using the one. The next priority is the ADCs. I got to get it out of the result buffer within 320 nanoseconds. I don't want to miss it. So that's the next higher priority. And the lowest priority is the UART. It's only running at 139 kilobytes or 1.25 megabaud, 9 bits to a byte. And UART has an 8-byte FIFO in it. I have tons of time to get that out of the UART. So it's going to run at the very lowest priority. So it can be stalled. Okay. Yes?
Is there a reason you didn't use built-in USB that we won't forget it's would that be faster?
No.
Okay.
The USB stack is going to take CPU time. So I let the FTDI chip do that. Yours is simple.
It also uses our more DMAs.
Yeah.
What
they're dedicated DMAs.
Its own built-in DMA.
Yeah. So
It's separate from the pool of 8.
But
Okay.
it would screw me up with all of that logic, and it might drop my sample rate down because those DMAs are going to compete for buses. So it could do that damage.
Yeah,
But
I can tell you it wouldn't have worked, doing the LED cube, because you get endpoint 0 transfers that are occurring every millisecond from the VC, and the USB DMA has no choice. Eventually, even if it's lowest priority, eventually it has to put that data somewhere to respond to the PC, and that's like a 64-byte transfer. And so all of a sudden you're going to lose a 64-byte slot for the logic analyzer, for everything, and you're going to get all this skewing. So it was a very good decision not to use USB on
Right,
this. I asked you the same question, by the way, right up front.
And I just said, I'm offloading.
Yeah.
And remember, the MZ USB stack you just got running.
Yes.
So I didn't, and no, I am not running Harmony in this. This is all this code I wrote. In fact, all of this code I wrote. So, and I was not up to speed on it, so I just put that in and I just offloaded it. to UART is pretty simple.
If you'd have used USB to UART, it's the same type of chip, you wouldn't have had that problem with yours, right?
That's correct. Yep, that problem would have been eliminated on the cube if I used the USB to UART, but I'm running the USB harmony stack on the LED cube, so I suffered these
You
issues.
suffered the problem, and you hit the problem.
Yeah, I ran into the problem.
Right.
Exactly. I got around it because I had a FIFO on the SPI,
Right.
and that actually solved the problem on the cube.
But my
that won't solve it for you.
AWG in LA would not tell.
Nope, wouldn't have worked.
So, as far as interrupts go, I think I told somebody there are 3 interrupts in the system. There's actually 4. Sorry, I forgot the Wi-Fi one. There are 4 interrupts in the system. I want you to know there's no timer interrupt in there. There's nothing in here about timers. The core timer will roll once every 42 seconds. I put the updating of the timer in my loop, my loop task function, because I got my loop time is more than 42 seconds. Fire me and fire somebody else. So I do the core timer in my loop task. I got that timer out of there. These are the only interrupts I have in the system, and I gave them priority. And the Wi-Fi's got the lowest priority on the interrupt system because the Wi-Fi module has cache in it. It's really tolerant to being slow into getting it. So that's the lowest part. That was a dead simple thing. But these other ones actually, I had to think about them, the order. And they look like they might be backwards, but they're not. I can walk through it. Remember on the oscilloscope, the way the oscilloscope works is the first interrupt is if I'm using rising edge triggers. The first one is when I'm below. And the second one is with the trigger is when I go above, and that's how I know about rising, because I knew I was below, and now I know I'm above. And then the third one is this delay timer to actually tell me to stop acquisition. And that's the third one. What can happen here is the first one fires when I'm below, and I turn on the second interrupt. What happens if that second interrupt occurs right while I'm still inside the first interrupt? Well, it preempts it. And I do not disable interrupts in the interrupt routines. Absolutely not. It could preempt it. But you know what? On that first interrupt routine, the only thing I got left to do is epilogue code. Yeah, if you want. I already turned on the second one. That's all I really need to do. So epilogue code can work. So it can preempt. So the second one comes in. Now the second one's the trigger. Well, what I do in the second one is I take the DMA pointers, and as soon as I take the DMA pointers, I turn on the delay time, the end of acquisition. Well, let's see what happens. Let's say the acquisition delay timer occurs right then, right before the second, before I even look to see where the trigger is. Let's say it happens right away. It's just going to turn off the DMAs. Well, guess what? The DMAs are frozen. I can still go back and look for the trigger point because they stopped. They're not going anywhere. And if they didn't trigger, that's fine. I'm still going to go back before the DMA gets overwritten, the buffer gets overwritten. I'm going to go find where that trigger point is, and I got a little time to do that. But I got to do that in your too. But so fine. So let's say it goes, and it's fine. Now I come back to the first one. I go back. I look for the trigger. Everything's fine. I get it. I mean, now I can calculate all my times and stuff. And then I return from that, and then I go into the first one, and all I got to do is execute the epilogue code. So this is the right order to run these priorities. And none of them have to disable interrupts. So those are the interrupt keys. Let's talk about USB serial. This is easy. Talked about this. I put an FTDI chip down. It offloads USB stack to the FTDI chip. I can also offload everything for like negotiating for 500 milliamps. I can put the Digilent name in there. It's great. And I can now talk USB, which is a simple peripheral on the MZ. I run it today at 1.25 megabyte, which is 139 kilobytes per second. What I did in the G that hasn't come out yet is I tied the oscillator of the MZ to the FTDI chip. The MZ runs at 24 megahertz, and the FTDI chip runs at 12, so I put flip-flop in there. And I just turned my asynchronous protocol into a synchronous protocol, because both the clocks are now in sync. And by doing that, and also by picking dividers in the timer, very specific UART speeds that that I can hit dead on with the timers, I can actually jack that speed up to 500 bits per second successfully. And I do this on Wi-Fi too. So we hope to increase the bandwidth of the USB mechanism by a factor of 4 in the future. We do require USB 2.0 high speed. Full speed can't keep up. It should. You look at the numbers, you think there's plenty of bandwidth, but it doesn't. It doesn't keep up. You've got to go with USB 2 high speed or USB 3.0. Through the UART, we have our communication. If you just power up, if you can say put TerraTerm on and set your baud rate to 1.25, which you have to manually click in, and you power it up, you're in menu mode, you're going to see a whole bunch of stuff. You're going to see all of the internal voltages with 3.3 volt rail is with a USB minus rail. You should see that all scroll by as it calculates it. And then you have for early debugging, early coding, I had menu mode where I could do things like set the Wi-Fi parameters. And then later I added the JSON mode, which you can pop into, and now you can actually send through TerraTerm JSON text through the UART to do that and communicate to it. The FTDI bus, the FTDI chip also negotiates 500 milliamps on the bus. I'm technically out of spec because when you first plug it in and I haven't negotiated, I am drawing more than 100 milliamps, but then shortly after the FTDI negotiates for the 500. So there's a little tiny, and it just never seems to fail. Wi-Fi for years have been drawing 120 milliamps and nobody's complained. So, and it also provides, the FTDI chip can provide some serial numbers and stuff to the USB, to the host. So how does the UART work? We've got the UART peripheral. We got both transmit and receive. There's an 8-byte FIFO. Whoever did the UART peripheral did a good job, because if there's 80 bytes in the FIFO, I continue to get interrupts. So I can pipe that directly into the DMA, and even if I'm 2 or 3 bytes behind, I will continually get events until that FIFO is empty, so that I don't miss anything. This will trigger as long as there's a byte in there, this guy's going to trigger. So zap it. You know, the data comes in, it goes into the FIFO, and you trigger the DMA, I put it in my result buffer. Likewise, anything going out, I put this up, I just set up the DMA pointers to the UART, and then I forget it. I just let that buffer drain, because the DMA, whenever there's an open slot in the transfer buffer, the DMA gets a trigger, a light goes over. Waits until there's an open slot, gets another trigger, and goes over until it's empty. I don't, of course, run the DMA in circular mode. I run it till completes. And so that's how I get the data in and out. And of course, I can get tremendous baud rates with this because the CPU is not involved, but the DMA is involved. So the protocol, whether it's through Wi-Fi or USB, is text-based, and it's JSON. It's a JSON syntax. Started out pretty simple, it's now pretty complicated. We added a lot of commands over time, too many. One of the biggest pieces of code in the OpenScope is our server commands. However, I don't care where I get yes?
How big is OpenScope today in terms of the code size and RAM? Do you have a feel, approximately?
It's a half an inch. A little less when you turn on optimization. I don't, well, by the way, OpenScope runs unoptimized totally. It's compiled OO. So everything you're seeing today is compiled OO. The reason why is the CPU execution time is not particularly important because everything's running in the peripherals. And the reason I kept it OO, I'm being convinced by Jason to go to O1 because it's still free. It's because on the XC32 compiler, OO is free, so is O1, and there is actually, it goes down to about 350K if I go 01 from 500. So there is a, but I want to make sure that anything I publish and run, you can compile and run with the free compiler, because I don't want you to have to buy the compiler to build this thing. So I just did everything with it. And what you're seeing today is all compiled below. So, and it's only a half megabyte flash. I got 2 megabyte flash on the MZ, so I don't need space.
Just a little bit.
Yeah. Now the RAM, that's a different story. I got 512K of RAM, and I'm using about 512K RAM. Early on, I still have serial prints that'll come out if you use TerraTurn and see serial prints. When you turn on JSON mode, those will quit. Those will block. But obviously, early on, I really wanted to see what was going on, making sure everything was fired up properly. And it's less important now because the code works. And I also, like I said, I had early on, I had this serial-based menu mode, which is still there, but it's a limited command set compared to the JSON. So you want to flip directly into JSON mode and start working JSON, because that's really where it comes in. Here's, an example of JSON. You want to do a demo at this point?
Did we have a slide for the demo or not? I can't remember.
There you go. There's our slide.
Nothing like a little bit of leading here. So, oops, shoot, that's not what I want. Just give me a second here. Source.
Do you realize I had to get that photograph approved by legal?
Did you really?
Yes,
I did. For anyone else, believe it or not, that's the first computer I ever programmed was the TRS-80. I'm not kidding. I used to hang out in Radio Shack and program it. So that's actually where I learned how to program computers. It was in Radio Shack. So that was only like 2 or 3 years ago, right?
Well, we know you were always this way, John.
So why did you have to get a picture of that approved by legal?
Because images are protected.
Sometimes lawyers.
Yeah, lawyers have to be paid.
So, I just want to show a couple things. It turns out that you can directly talk to OpenScope if you want to through a UART. I'm going to connect to it through a UART, and later on,
we're just going to do the whole thing. We're going to just do the whole thing.
Okay. Do you want me to start by showing
you
UART
do your
stuff?
thing,
Okay, I'll do my thing, and we'll flip over to yours. Okay. So, yes.
You may want to shrink the resolution a little bit because you're way overhanging the screen.
Oh, don't worry about the left. This isn't so important to you guys. I think I'll just move this one over just so you can see it. Yeah, thank you. So first thing I do need to do is because I was using OpenScope before, I'm just going to get rid of it for now. Right. I need to disable the Digilent agent. So once OpenScope fires up, then it connects to COM7. It finds a COM port, which is the FTDI that's been enumerated. It locates that, and then it creates a HTTP socket for that Waveform's live will ultimately talk through. Now I'm going to actually talk directly, send JSON commands directly to the COM port through terminal. So I need to go over here and release, and that releases the COM port. And then once I do that, now let me just clear the data and options, and I should have a COM72. And as Keith mentioned, the baud rate is 1.2 megabits per second. And click on OK, connect, and now I'll hit. I'm just going to do a quick reset of OpenScope. It's always a good idea. Now you can actually see OpenScope.
Yeah, and you can see the voltages right here. Oh wow! Look at your USB. You're overvolt. You got a full 5.
Isn't that awesome?
Yeah, you got a full 5 volts on the USB, 3.3 on the 3 rail, 2.999 on the 3 volt rail, and 1.5 on the 1.5 rail.
That's why I like this laptop so much.
Yeah, that thing is really, I've never seen 5 volts on the USB. Never.
So the first thing that you actually have to do to enter is if you want to play around with JSON controls, you have to enter JSON mode. So we'll hit a 1, and now we're in JSON mode. And at this point, we can completely control the OpenScope. So we're going to start with basically doing, this is a JSON script. And this script will basically do the get NIC status. So this will find out what the status of our network interface is. And I haven't, for some reason my IP address is all zeros, so it hasn't connected to the router.
You just rebooted it,
I did, yeah.
we're gonna have to make sure it connects to the router.
Yeah, because it didn't connect to the router.
No, it did not
should.
connect to the router.
Yeah, it should
Here,
have done
let's
that.
reset it. Hold on. Did my router go down? I hope not.
I wonder if your router went down, yeah.
Let's see if we can get it to connect.
Is it gonna mess anything up, like say your SD card?
There you go, we're connected.
Okay, so it's good.
So do it again.
Yeah, so we'll hit 1, and
Push that back in there.
and so now we can see, so we did a get network status, and you can see the IP address 192.168.1.10, and then we can see, it's connected to the Digilent AP. You can see the AP's advertisement. We're using WPA2 and so forth. But as Keith mentioned, there are literally dozens and dozens of JSON commands to control OpenScope, and everything that we showed, we demonstrated this morning. When I set the AWG, for example, for a specific frequency and amplitude, that was just a regular JSON command. So OpenScope doesn't really know that I'm going through the terminal right now. The GUI would have done the same thing, and so everything that's available is there. So the next thing we'll do is calibration. Since Keith spent so much time with that crazy polynomial formula, you can do a get calibration, and then it will dump all of the calibration parameters that OpenScope is using. So all of those coefficients, those A, B, and C coefficients for that polynomial, those will all get dumped here. So you can take a look at those. Not that it's really important to you, but it was very important to Keith when he was debugging OpenScope and making sure the calibration worked correctly.
Well, let's stop here for a second. Why not? Let's look at some of these numbers. 0.5% off. 0.5% off. 1.3%. Those are the numbers we're getting. But when I say off, it's off from ideal resistors. It's not that it's off. It's not like your error of the scope, and your scope is accurate. It's what is compared as if that was an ideal. So all the resistors were perfect.
So in other words, remember the PWMs for offset that Keith had and such? So he is compensating for all this. This is just, if he didn't do any compensation, this is how far it would have been off. And, and then with compensation,
it's dead on.
It's pretty much dead on. But it's an interesting, it just sort of tells you how well the design is working, for the compensation, and how it would have been with and without it, which is kind of a very, very interesting point. And from there, you can start actually controlling instruments if you want to. So this command, if we take a look at it, will stop the AWG, and then it will set a regular waveform to a sine wave at
1,000 hertz.
1,000 hertz, thank you, because it's in millihertz, and I always keep forgetting that. And then 3 volts that it's set to, because that's in millivolts as well, and then a command run. And so, so if we grab this JSON command and send it over here, I'm just going to clear the data again so you can see it. So then it will respond back and say, hey, here's my command, status code passed, and then the AWG is set. And if I had a scope on this, I would actually see that the AWG was exactly that.
Yeah.
And so, so with that, I think we're going to now.
No, well, why don't we just go ahead and go back into the
Waveforms Live.
Waveforms
exactly.
Live. And then I'm going to do it from the Wi-Fi.
So now I'm going to actually go back to Waveforms Live. So I just killed my my terminal program, so COM72 is no longer in use. And so now.
So what happens if you run the logic analyzer and execute that command?
It would return an error. The status code return would say instrument in use. It would return the status code of instrument in use. Yeah.
Exactly. So so now hold on a second. I just want to configure the AWG to the scope. So just give me a second here.
Stuff
the feedback. Well, because we were doing a different demo.
Sure.
So these two puppies are now connected, and so I'll just do a quick test and make sure that I'm just going to turn this guy on and hit run. Okay. So I can see that this guy is working now.
Put it to a different waveform.
Let me stop this, and so I'm going to stop, and I'm going to do a triangle wave. And
do a run.
Hit run. And so I can see I've got a triangle wave right now. OpenScope's running just fine. Everything's working great. And Keith is now through Wi-Fi.
Yeah, I'm over here in Postman. If anybody knows what Postman is, Chrome extension.
Hopefully everybody can see
Yeah,
Postman over
Postman
there.
over here. And this is that same command that John just sent, stop. I'll stop the waveform generator, I'll set it to 1000 hertz, 3 volts, peak to peak point. But now I'm going to send it over Wi-Fi to that address. So, actually all I'm going to do is say send. And you can see I got the results.
And look at that.
Look what the
So Keith just changed, so remember we mentioned that the command interpreter has 2 channels, come in through Wi-Fi or come in through USB, and it doesn't care. And it's not necessarily committed to one channel or the other. So Waveforms Live that you see here, the GUI, is getting all the data that you see through the USB port. And Keith just sent an AWG update command. So he did the same thing as I would have done. So if I did this, that would be the equivalent of stop. And then now what's interesting is my GUI, I would have done this and then restart. And so Keith just sent the equivalent JSON commands to what I just did. A stop, set it to a sine wave at this frequency, and then restart it. I'm sorry, question?
So if you have Waveforms Live running over Wi-Fi and locally on serial at the same time, how does it know which one to send a command back, like the results?
There's currently no synchronization. So what will happen is the UI will get out of sync. But there is a refresh command that will reestablish. So like for example, if you shut down Waveforms Live and then start it up again, it actually queries the scope, every instrument, to see where it is. Now it won't get your scales right, but it'll get what the scopes are doing or what the channels are doing. It'll get that right. So you might come back, because you can set whatever scale you want, and it doesn't know what that is, right? But it'll know what the scopes are doing, and it'll sync up to that. So we'll query it and ask it. But if you just run them both at the same time, yeah, the UIs are, and we didn't synchronize that. That's task for another day.
So that would mean that if you have multiple web clients trying to connect at the same time, that's also not going to be.
They're just going to get. They're going to get. But in many ways, it'll kind of work. I mean, it does. The instrument doesn't crash. It's just your UI gets out of sync. And in fact, let's see here.
You actually wouldn't even necessarily want them in sync, because let's say you're having 2 people viewing the same instrument, then that person may want to actually look at the screen differently than I'm looking at it on my screen. And if you were syncing them, you wouldn't be able to do that.
Right. So
That's true.
I just connected over Wi-Fi to his scope. Okay? And it's really not having a good time with it. So
I'm not surprised, actually.
yeah, but I got control. I got it. And so now I'm running, and then this is all over. Now I want to show you something. This is all over Wi-Fi. Let me do a run. That's the update rate. Okay?
Something tells me you're connected to that scope and not this one.
No, oh, am I?
Yeah, I think you're connected to the wrong scope.
Oh, dang. Let's try connecting. Okay, now I'm connected to his. Okay, there we go.
Incidentally,
Okay.
Keith is doing the faux pas that you never do. We have not tried this before.
No.
So.
But anyway, here's your update rate over Wi-Fi to his scope. Okay, now let's do something fun.
My scope, notice though, has been perturbed, if you notice. So.
Yeah, it's unhappy, right? So.
Speed is USB faster than Wi-Fi.
Now I just hit run, and I just saw the fact that Keith changed this to a sine wave.
Yep.
Now notice, so that's okay.
See, as far as the OpenScope is concerned, it's just getting commands.
I'm sorry, Jeff. I didn't hear your question. Sorry.
Speed, do we want to run it over Wi-Fi because it's faster, or USB because it's faster?
USB is usually, depends on your if you're USB 2.0 or whatever. Usually USB is ever so slightly faster than Wi-Fi. Now, you can run a really slow Wi-Fi connection and it'll be crappy.
But it'll get even faster on USB
when I up the baud rate, yes.
Yeah.
So USB. But it is, come on. This is not bad over Wi-Fi. That is not a bad rate. Are you doing it too? Are we both doing run?
We are. We're both. I'm doing.
now
I
that's
don't.
kinda-
I don't think it likes. Let me put it this way. I do not
it's
believe.
working. It's kind of working.
Oh wow, we're both.
fighting
No,
each other.
no. Here's the problem. As soon as you hit run, mine stops. As soon as I hit run, yours stops. So the answer is we cannot have both at the same time, which
But
sort of makes
more
sense.
importantly, it did not crash.
Right. I think what happens is with run, no doubt the browser once you hit run and it just it crashes as soon as it does a response to you, I time out and then my run stops. That's what's happening.
It says idle this.
Yeah, it's pretty graceful in the way that it. So now here his goes to idle mode. Notice. So.
Well, actually, I clipped it.
Oh, but that's okay. Hit run now, and you're going to force me to idle. Watch. See, I just went idle now.
so-
Everybody
Both
see that?
going over the Wi-Fi or?
No, I'm
No, he's going
and
USB. I'm going
Wi-Fi.
over Wi-Fi, so we're competing.
I think you only have can you handle more than one Wi-Fi connection simultaneously? I don't think.
Yeah, absolutely.
Okay.
Not a problem.
So I guess we could have done that.
Yeah, not a problem.
Which means we could have 3 of them going at once.
Yeah, well,
more.
and I'm making no guarantees on the collision of the protocol. So, all right, so we're going to zip through because we did a bunch of these slides. We did the HTTP server. So here's something. This runs the HTTP server I wrote a couple of years ago. I actually presented a network class. It's on your thumb drive. Is the class that we did back in 2014. That's my network stack and HTTP server. That's what we're running. We're running a derivative of that on this scope. So if you want to look at all the network, I mean, I don't want to do a whole class on network. So if you want to look at those slides, you can. We support static web content on the SD card. So if you want to put the OpenScope or Waveforms live on the SD card, you can do that. You can serve it up from the OpenScope. But you don't have to hit the digital servers. The HTTP server supports dynamic content as well as static content. We run the Digilent IP network stack underneath it. And this is what provides the base interface. We did the Postman thing. Let's talk about what can you do with this. If you run, you can get all the content directly off the OpenScope, like I said. And the way that it works is if you hit the IP address of the OpenScope, it will return a redirect page. And I actually store that in Flash, so you don't even have to have the SD card. And the redirect page will say, go to the Digilent server to download Waveforms Live. If that fails, it will then try and get it off the SD card off of the OpenScope. So the problem is when you download the content off the OpenScope, it takes about a minute. It's a lot. Waveforms Live is pushing 4 megabytes now. Yeah. It's a lot for that little guy to ship over the wire at you. So it takes about a minute for it to get. But it gets there and it works. So you can put the content on there. But you need an SD card, obviously, to do that. With the redirect page, if you're connected to the internet, you can still hit the OpenScope with the IP address, but it'll redirect you to the Digilent server to get Waveforms Live. If you want to explicitly take Waveforms Live off of your SD card, just put the index.htm after the IP address, and it will force you to get it off the SD card. Like I said, OpenScope can serve up Waveforms Live. Waveform Live works on most browsers and phones. Because you can have the content on the SD card, you don't need to be connected to the World Wide Web. And if you start your phone as a hotspot, you can actually connect the OpenScope to your hotspot and then run Waveforms Live off the SD card on your phone, and you can run that off a USB battery. So you can go out in the middle of the woods and use this thing and you're totally isolated and you don't need to have internet connectivity or anything. And then, of course, if you download the iOS app, you don't need Waveforms Live because it's enabled now on your phone. You also have a memory app you can download. So if you put the USB battery, drive it with USB battery, drive it with Wi-Fi, you're totally isolated. So here is the configuration that we had. This is actually a photo we put on the Kickstarter, a photo we actually used on our website. We got our USB battery driving the OpenScope. We turned this into a hotspot. We connected the OpenScope to it. And we powered John Day's little metal detector off the OpenScope, which of course comes from USB battery, and we got our trace on the OpenScope. So totally isolated and disconnected. All right, Brian, I did the right thing.
Good for you.
And I did it out of the box. I didn't even have to change it. We were talking, Brian and I were talking about open hardware, and I didn't say open hardware. The firmware is fully open source. What this means is under MIT and BSD. The source is available, it's on GitHub. You can download it. We've already had people build it and program the OpenScope. You do it through the Arduino IDE. There is no GPL or LGPL in it. It's completely stripped out. What that means is you can use this code for commercial purposes. You do not have to publish your code. If you take code out of this, put it in your readme file, you do not have to publish your source code. You can take whatever you want from it.
Keith, I'm a huge fan of bullet number 3 there. Infectious licenses.
That's a good way to describe it. Yeah.
It is, but well, GPL is infectious because it forces you to publish your code. And we're not doing that.
Viral.
Viral. So, the only thing is that we do require attribution. And it can be as simple as a line, a bullet item, it can be a file with your sources. It just says somewhere you have to say, we picked up Digilent code. Okay? So you do have to give attribution. The hardware, I thought I said open hardware, and I did not. I'm very glad after our conversation. The hardware is Creative Commons. What that means is you're going to have to retain the Creative Commons license if you do hardware, and you're going to have to give attribution. We do not publish project files, we do not publish the Gerbers, we only publish the schematics. We're having some problems with some knockoff.
And the t-shirt.
And the t-shirts. We're having problems with people knocking us off, and we just decided we're not going to publish the project files.
Is that knockoffs in the U.S.?
No, China.
You know, but selling back to the U.S.
Oh, of course. Of course. Yeah. So we're not going to publish, we're just going to publish the schematics. Don't publish the Gerbers, don't. But it is under Creative Commons, so you can take the schematics and copy them and lay it out yourself. The OpenScope builds natively, and obviously did almost all of my development in MPLABX. I couldn't even imagine doing this anywhere else. So it builds under MPLABX. It builds under the XC32 1.3 compiler or newer. It uses the new lib option, which means we use the open source new lib libraries. We do not use the proprietary libraries. You can build this under Arduino. We'll talk about that here in a second. And we don't use optimization. If you're going to build this under Arduino, you're going to have to download the Digilent core. It won't work under the ChipKit core, or might not work under the ChipKit core. And the reason for that is, well, I'll get to that here. When you program from MPLABX, all flashes will waste. It's going to kill your bootloader. There's a bootloader on here. That's how we update the flash. It's going to kill it. But the MPLABX project includes bootloader, so when you reprogram, you'll reprogram the bootloader along with the code. So one of the problems is we put Wi-Fi parameters in flash with calibration parameters in flash. So if you program from MPLABX, you're going to wipe those calibration out. You're going to have to recalibrate every time you run the project. We have the options in Waveform Live to say, don't put those in flash, put those on the SD card. But you don't really want to put your Wi-Fi parameters on the SD card because you just made a public. But you can for development, because that way you can continually reprogram from MPLABX, and it still will have your Wi-Fi parameters, it still have the calibration data, but it'll have to come off the SD card. When you're done, you've got everything working, you put it back in flash and throw the SD card away, fine. But because MPLABX wipes the flash completely, you're going to lose all that. However, if you use the bootloader, like when we do an update over the internet that uses the bootloader, it will not wipe the calibration, it will not wipe the Wi-Fi information, because the bootloader only programs the pages that are updated. If you're going to program this as please remember to get your pin 1 lined up with pin 1 and don't flip it over. That's all this slide is about, is to make sure you get the ICSP port correct. And that is little thing about, you see this PIC-KIT 3, we don't see an ICE3, we don't see a real ICE there. You can, but your analog is going to be messed up. Those have FPGAs in them, and they're really hard on the ground, it really jerks around. A lot of spikes and noises. And so I was not able to develop this one. I had to use PIC-KIT 3, this was fine. And it's all ground noise. And it's unfortunate, because it's slow. So the Arduino environment. It will build under the Arduino. You have to use, right now, that I know of, you have to use 1.6.9. The project setup has subdirectories. And Arduino 1.6.9 built subdirectories properly. When CC and ORG merged, they screwed it up. And I don't know if it's been fixed or not. Has it? But if you're going to build this through the Arduino IDE, you have to use 1.6.9. Anything newer, I don't know that all bets are off. You have to download the Digilent Arduino core because, you know, when you talk about an open source community like ChipKit, a lot of hands in it, a lot of cooks in the kitchen, and you keep, you know, occasionally something gets broken and it doesn't work. And sure, they're active in fixing it, but there's a time when it might be broken. So we just said, fine, we're going to freeze it. And this literally does pretty much have a snapshot of the ChipKit core support. We fixed everything that didn't build, so it would build, and it'll build under that. So I think at some point in time, all this will get fully resolved, and you could use the ChipKit core, but we just have a stable snapshot for it.
Is your board manager in the board manager Arduino IDE?
If you put the URL in, look.
So you do have to put in the URL.
You got to put, and the references I give you the URL.
All right, cool.
Okay. The OpenScope uses nothing from the core, the Vision core, ChipKit core, whatever. Absolutely, it's a completely standalone project. Everything you need is in the sketch. Okay, everything, right down to the bare bones. Almost. Except for CRT-I.S, that one will get sucked in. And MPLAB-X gives you an equivalent copy of what the core will give you. But other than that, nothing gets sucked in from the core. So if it builds at all, it's going to work. Because all the code is local. In the INO file, let me say, you know, MPLAB-X doesn't know anything about INO files. There's no code in the INO file. All the INO file does is tell Arduino, bring in these libraries, and that's all it says. So it really is a standalone compiler project. One of the differences, say, between the ChipKit core and the Digilent core is our Digilent core uses the official XC32 1.43 compiler with the new lib option. The ChipKit core uses a ChipKit compiler, which is very similar. There's nothing wrong with the ChipKit compiler. It probably worked just fine. But we wanted the MPLAB-X project and our Arduino project to actually use the same compiler. So we put in ours, we did have to strip out all the proprietary library stuff from it because there is proprietary library stuff in XC32, but we just stripped it out. So it's all open source. Everything here, and of course if you don't know, the XC32 compiler is a unique compiler, it's open source. So we put that in. Of course we had to put attribution to it. We definitely use the new lib option. This is why we have to use 1.43 or newer, because that's when the new lib option came about in the compiler. And that uses the open source libraries. Like I said, we don't compile with optimizations, so you can use the free compiler. And that's true with MPLAB-X core and Arduino is the free compiler. The two mechanisms, MPLAB-X or the Arduino builds, they are substantially the same code. That is the same compiler. They generate the same, they compile the same sources, and you end up with the same .s files or the same, you know, intermediate files. The difference is the link order could be different. So one thing you get is maybe the link order will be different between the two, if you do the two. And if you're doing real hardcore development, other than just, hey, I want to compile and run it and maybe look at some stuff, I really suggest you do this in MD.X. It's a big project, lots of stuff, and X is really where you need to work this, because the Arduino IDE just offers you no help other than to look at the source and compile it. And here are the resource links. You know, the general documentation. This is the top page. This is where you can get the firmware. That's the compiled firmware. The sources. Let's see if I can find. Here's where you can get the Arduino IDE. Here's where you can get the digital core. This is the thing you would put into the board manager, or into the I guess it's actually platforms.txt to download it. So I think we covered everything.
Nice. And you're exactly 8 minutes early.
And that gives me just enough time to talk about